Okay, here we are. So I'm Alessandro Antonucci. This is the whole bunch of slides we are using for today. So maybe you can download the PDF from this QR code. I'm using also some Python notebook, just some additional material, and this URL. Sorry, I didn't organize in a better way, but if you go to this address, you can download everything. But probably what you need the most just to follow is this PDF. And from the PDF, you can also access the notebook and the material. And at any moment, I can go back to this slide. Okay. Of course, I would like to keep these 4 hours very informal, so you can stop me any moment for questions, for comments. Today is supposed to be the AI day, so I'll try to be very practical, in a sense. And also, sometimes I'll try to keep things very, very simple. So maybe for some of you, I'm going to say very, very simple stuff. If it is too much, stop me, tell me this is really too simple. I want to cover many different topics, but my goal is also that you understand something that you can really use in practice. And okay, especially in the second part of the talk, I'll go to more sophisticated, more advanced topics. But especially in this first time, I will be very high level and probably too much for some of you. But my interest is in giving you an overview of what AI is now, what probabilistic AI is nowadays, especially in the last days, and what has been done about the connection between AI application and imprecise probability theories. And my focus is, of course, in probabilistic AI, and more specifically, my focus is on graphical models, so which are a typical, powerful approach to probabilistic modeling. So I'm most of the time talking about probabilistic models based on graphs. In a sense, I'm going to detail in the next 4 hours. I know today is the kayak day, so I cannot compete against kayak, but I try to make these 4 hours not too boring. And of course, again, if it is too boring, stop me and say, come on, we should say something more appealing and more challenging for you. And before starting, let me apologize for being late. I was not able to be here from Monday. I was in vacation. This is a motivation. Not sure it's a good excuse, but was motivation. I have evidence. I was in holiday, and you can say that I was not too far away. Not sure this is Dutch. No, it's not. Maybe it's old Dutch. You can say maybe I was somewhere here in the Flanders or in the Netherlands. No. A better excuse, I was more far away, I was in Malaysia, but this picture is in Malacca, and there is something from the Dutch times. It's not Dutch, maybe it's old Dutch. Oh. But you can, it sounds Dutch, no? Okay, let's start. And okay, this is more or less, I'm organizing my material in 8 different units. Okay, this is the very compact formulation of the topics, but I can be more explicitly. So the very first, let's call it module or unit, will be on will be very short and will be on precise probabilistic. I know you already did an introduction day with Eric, but it's just to define a little bit the kind of notation, the kind of terminology. So I need something like that. Also, from a practical point of view, I want to do some very small, very quick exercise with you. Then, okay, today is the AI day, so I'm supposed to tell you something about AI. I'm supposed to tell you something about deep learning. I will try to emphasize that deep learning is not all AI is about. There is something more. Of course, deep learning is very important, but I will insist a little bit on this topic. This will be a very qualitative overview. Then I want to move to graphical models. I will start from precise. graphical models, and then I will show you in which sense these precise approaches have been extended to imprecise probability, and the resulting model, the extension of Bayesian network, is called the credal network. And I will tell you something about these imprecise probabilistic graphical models. Then something about the application. I did something in decision support, which I think is kind of old-fashioned, but still, from my perspective, important. There are many applications, decision support expert system. I'll tell you what has been done, what can be done in the field of machine learning. And this will be the last unit, and for me it's most challenging because it's what I'm also working on more recently. I will spend like 1 hour talking about causal analysis, which from my perspective is very important for contemporary AI, and the connection with imprecise probability, and more specifically the connection with credal networks. So this will be basically in the afternoon, the slot of the afternoon. So this is my plan. Not sure I will be able to be very, very precise, but let's start with this first slot and the first 2 units. Okay, the first unit I use, okay, maybe now you can understand this. I want to make things complicated. It's just standard probability theory, but for imprecise probability, precise models are in the upper and the lower. They should not be equal, but in some special case they are equal, and so we call this precise model, linear prevision, or whatever. And I just need 1 slide just to define a bit of common language. You know, with my colleagues in the previous day, you used also more sophisticated formalism. I'm very loose. I'm not using prevision. I'm not using a set of gambles. I'm just using probability. And for me, you will see the imprecise probability is basically just a set of distributions. Just a set of distribution for which you can say that this is more likely. There is no second order knowledge. U of knowledge is not a single distribution, it's a set of distribution. So this will be in all the 4 hours my model, my imprecise probabilistic model, which is what you call also a credal set, if you want. Okay, let's say x is my variable. Let's say omega x is the set of possible values. Most of the time in these slides I will focus on discrete variables. And in some cases the results can be easily extended to the continuous case. In some cases they are not. So most of the time we assume everything is a discrete setting. So our precise uncertainty model is just a probability mass function. So it's just a function that assigns a different probability for any different outcome. So it's non-negative, it's normalized, and so this is what I call a PMF, a probability mass function. No more than that. Tossing a coin is biased 0.7, 0.3. This is my PMF. Okay? And okay, of course I'm interested in computing expectation based on this uncertain knowledge. If I'm certain about the state of my variable, and if I have a function f of the states of my variable, I can compute the corresponding value of the function. But if I'm uncertain, what I can compute is just the expected value, which is just a weighted average of the different value of this function weighted by the different probabilities for the different outcomes. Really no more than that. If you want, you can see it's kind of linear functional. Okay, this is for a single variable. We can consider a joint setting with 2 or more variables and define a joint probability mass function. There's really nothing more than that. So if I have a joint probability mass function, I can do an operation which is called marginalization. So I can just sum out the variables I'm not interested. So I take the joint, and I'm interested only in x, so I sum out y. This the marginal knowledge I can start from a joint distribution. And I'm also interested in conditioning, no? So maybe I have my joint probability, and I can compute the corresponding conditional probability. So I need the margin, so the probability of the conditional event on the denominator. And basically, if this is strictly positive, I'm not considering the case of conditioning on zero probability events. I can compute this conditional probability. You see? It's okay? So just kind of standard stuff. Okay, guys, maybe if you manage to, you're using, you all using collaboratory, Google Drive, or some Python stuff. It's not that we all should do. I will show you something, it's not. But if you want to do that, one option is to download the PDF, if you use Colab. And where in this PDF, this, for instance, is an active link. So you can click and open a Colab notebook. The other option is just to go to alessandroantonucci.me/ai_zip and download all the stuff, and you will have locally the notebook. The third option is just to check what I'm doing together with me. So I'm not waiting you. I'm just showing just to make more practical the feeling about what we are doing. And if you need me to go back to this QR code or to this URL, just let me know. Okay. So say that you are already expert of Colab, but okay, Colab is just because it's simpler, you don't need to install, but maybe you prefer to use some local Jupyter, whatever. Okay, I just want to use some data. So click on this if you have the PDF. This is a link, or just open the notebook, or just follow me. A second. And there is this notebook, and okay, what I'm just considering is a data set. So this is a data set of fake. No, wait, maybe these are real data. These are real data. This was an observational study. I don't know the detail of the treatment, but it's medical data. So treatment and recovery. 700 patients. So these are the counts. And we have an additional information, which is gender. So each variable is Boolean, say. And so we have 8 possible options, you see. And so we have data for the joint states of 3 Boolean variables. X is the treatment, not treatment. Yes, treatment. Recovery is not recovery of the patient after the treatment, recovery of the patient after the treatment. And gender, 0 maybe is man and 1 is woman, as I remember. You see? So it's just to play with some data. And let me tell you also that on Friday for the project, this will be an observational. This will be a pure correlational, a pure probabilistic analysis, what we are doing now. In the last slot, I'm moving to causal analysis, and the idea of the project for Friday is to do some causal analysis on real data. If you have some data set, maybe not too complicated because the project has a limited amount of time, we can use your data. If you don't, maybe we can use this very simple data set and to do some try to do some causal analysis by hand or with some simple piece of Python code based on this data. Okay, I need Python, so I created, and of course, if you can access this or if you downloaded, just copy and paste this, especially the boring part of the code, like the specification of this data set, whatever. So, you know, I need to import, I just need the NumPy, the mathematical library, and Panda just for the data. You know, the first time you connect, it takes a moment. Okay, and now I just load the data. So now Python has a data frame with all this data. And okay, let's say I'm not discussing a lot about the statistical learning of probabilities from data. We can do in many different ways. Let's say that I'm very loose. I just use the relative frequencies. So I have these 8 counts for the 8 different options. I just take the probability as the relative frequency of these 8 different joint events. So basically I divide by the sum, which is 700. And now if I print the data frame again, what you see is an additional column with the probabilities. This is we could call the frequentist probability, no? Because are just the relative frequencies. And this is a joint PMF. If you sum, the sum will be one apart from maybe some numerical rounding or whatever. Okay, you discussed the imprecise Dirichlet model. You said something in the... So with Matthias, so you know that's a natural way to learn imprecise probability is just extending a Bayesian approach. So let's also say that a frequentist approach can be good for this data because we have all the 8 possible outcomes represented because the model is very small. But imagine that we have 10 or 20 variables. Probably we are not going to have enough data for all the possible joint state of our model. Maybe in some case we have 0 count. A frequentist approach will learn a 0 probability, but probably this is not an impossible event. So it's much more reasonable probably to go for a Bayesian learning. So for instance, we can set a prior which is uniform over the 8 states, and we are basically smoothing this ratio. So instead of computing the ratio between the counts and the total number of observation, we are doing something like that. So this is the count, this is the sum, the total number. So the frequentists are just doing that. The Bayesian use an additional prior which can be interpreted as an equivalent sample size, so which a number of virtual observation, which is corresponding to our prior knowledge. Let's say we have S, but let's say S is 1, for instance. We have an instance which is not a real instance, but is the strength of our prior knowledge. So the total will be the real total plus 1. And for the different outcomes, we will have the relative strength for the different option set by a prior. Let's say we have uniform, so we have 1/8 for each different option. And so as a result, let's say that S is 1. This will be the real count plus 1/8. And on the denominator, the total count 700 plus 1. And this is Bayesian learning. And so these are the data. I said, you see, there is not, here we don't have okay, we have this count, so for this count the difference is not so small, but basically for this kind of data there is not much difference. In some other case, it can make a difference. And now let's say that we have our joint PMF, and okay, the observation, the operation we are interested in are typically the marginalization. So for instance, we sum out the Z. So we are not interested in gender. So given the 8 possible outcome, for each joint state of X and Y, for each joint state of treatment and recovery, we sum over the 2 different genders, and we get this probability and this probability. And now, instead of a distribution over 8 states, we have a distribution over 4 states. This is marginalization. Okay? And we can also do conditioning. I'm doing everything by hand. It's really by hand. This is just some function of Panda data frame. I'm just selecting the row of the data frame where X, which is the treatment, has this value, and where the recovery has this value, and then I'm summing out. So basically, I'm considering the 2 rows corresponding to gender, female and male, and summing the probability, for instance. And then, okay, this is conditioning, so I'm doing really by hand. I'm extracting these 4 numbers, the joint probability for X and Y, and I'm computing the probability for recovery, this one, recovery given treatment, and recovery given not treatment. And my data are telling me that if you do the treatment, the probability of recovery is higher. It could be tempting to say that because of that, we can see that the treatment has a causal effect on the recovery. But you know, with pure probabilistic approaches, this kind of causal conclusion can be very misleading. So it might be that really the treatment is affecting, but this is just a correlation. This is just a pure probabilistic observation. So giving a causal flavor to this kind of observation can be sometimes misleading, and this is what I'm going to focus in the last part of this talk. Okay, I was saying that this should be a 10-minute slot. It was more, but okay, I was kind of expecting this. This was just to define really a common language notation, some practical stuff. And now let's go back to the general topic. And the general topic for me is AI. And what I want to stress a little bit is that AI is not just about deep learning. I mean, now things are really a bit changing, but a few years ago, it was really crazy. So not most, but many AI conferences became kind of deep learning conference. Everything was just pure application of deep learning, because was the real boom of this application. And was also a bit of sad from the high level perspective, because was really just applying an idea and see that is very powerful doing application. I think now things are a bit changing. And this gives you also the chance to introduce in just really one slide my institute. I'm from IZIA, which is located in Lugano. Not sure Facchini said something about IZIA. I knew that. But okay, just let me spend one slide to introduce my institute. We are located in the southern part of Switzerland, very close to the Italian border. This is the Italian-speaking part of Switzerland. And this research institute was founded now a long time ago by this guy. And this battle is here because the guy was not a scientist, but somehow it was not, but was the guy who invented this drink made of aperitif drink, and so is kind of important for us. But this was a long time ago. Now, basically, we are a kind of AI department of the TU University of Lugano. Long time ago, we were a very small institute, like 30 people. Now we are growing because, AI is growing a lot. And let's say also that we have some, I would say, strong connection with this community. Alessandro, me, we always try to attend the SIPTA conference. Sometimes we also were lecturers at the SIPTA School. We organized together also with Marco Zaffalon, which is the director of IZIA. A long time ago, we organized the SIPTA. This was Marco. This was me. I organized the SIPTA in 2017. And I think we organized the first school. At that time it was called the Summer School. Still, we can call it Summer School or School. I don't know the official name. But just to say that we are very close to this. No, we feel part, come on, of this community. Jasper. So, what about AI? Okay, some people, I don't know if this is an important guy. Originally was with OpenAI, very enthusiastic, come on, about deep learning. Was saying that it's the new electricity, but apart from these sentences, come on, we had a very significant achievement, especially in the last 10 years. Okay, apart from image recognition, which is a kind of longer process, so translation. I don't know about if you remember, if you knew about that. This was okay. Was just an application of reinforcement learning to Go, which is a sophisticated board game, but somehow was important because chess was already solved by traditional AI, and so this was a very important success of reinforcement learning, achieving superhuman performance. Then extending this result to many, I'm working also in reinforcement learning, extending this kind of achievement to more complex setups is definitely not trivial, but was something important. Then, okay, I don't know about this. And this stuff has been achieved by DeepMind, which is now is a Google company. Some former colleague of us, former colleague of us was one of the 3 founders of DeepMind. He's very involved in deep learning. Also, our former scientific director is very, let's say, charismatic person, but also a bit controversial because he has very strong ideas, Jürgen Schmidhuber, about the strength of deep learning. And now, let's say, everybody is talking about large language model like GPT. So just say that deep learning is becoming very important, especially in the last year, if not especially in the last years, in the last decade, if not in the last year, 2 years. Okay, for some people, this is also, and this is from like a newsletter. This guy is, I think he's an interesting voice in the AI community. Is very skeptical about the LLM, large language model hype we have in the very last years, if not the last months. Now also there is some issue with this big company. They invested a crazy amount of money. So I'm not a super enthusiast, but I clearly see the success. You know, some people is saying, okay, like many years ago, there was the growth of AI, and at some point there was the fall of AI, because people had a lot of expectation about the potential, like in the 80s, the 90s, and then at some point they realized they invested a lot of money, and then they realized that everything was more difficult than what they expected. Maybe something similar is happening, but some of the results are clearly there. So probably there is still too much enthusiasm, but I think especially from a researcher perspective, there is still a lot of super nice, super interesting work to do in this field. Okay, let me, for some of you, this is very, very trivial, very, very naive, but I just want to say that what made deep learning emerging is somehow is a series of fortunate events emerging, because what I want to say that the theory, at least in some formulation, the theory of deep learning is not that, no, I don't want to say that it's not so complicated. Now there is an unbelievable sophistication, but the basic idea is really very simple. If you're studying in the first year of your bachelor degree linear regression, okay, it's just basically using some data to fit a model, a super simple model, learning a model from data, and this model is a predictive model, able to predict the value of y for an unobserved x, given a set of observations of x and y. And somehow, okay, this is what the deep learning is doing in a much more sophisticated way. The parameterization of the model is much more complicated. The idea was already there since a long time, but at some point, the new technologies started to, all these approaches, they need a lot of data. So at some point, much more data were available for the training of these technologies, and also better hardware was used to make the training of this model practical. I remember, like, it should be probably more than 10 years ago, some colleague of us at ITZIA buying GPU, which at the time were just for gaming. And they told me this idea of using GPU for massive parallel computing. And at the time, as usual, I'm very bad in predicting what is going to happen. I was saying, come on, this is a very, very stupid idea. And it was super, super successful and super smart. And then, of course, now the GPU are not the ones just for gaming, and also dedicated for the training on neural networks, and we had lots of successes. Okay, this is a very, again, super naive description of what a neural network is doing. So let's say we want to classify an image. And initially, the first strong application of neural network was basically in image recognition. And so each pixel is activating or not activating according to this function. So this is is intended to be a neural network after the training, and eventually you have a single layer making your prediction. So it's image recognition based on neural networks. But let me just define some common languages. So typically, at least initially, we are interested in predictive tasks. So we have data, and our data are annotated. So we describe the object we want to predict by a number of features, and I typically use this X for the feature, and we want to predict, say in a discrete setting, we want to predict the class, and the class is Y. We have this data, and from this data, we want to train a general model, and the general model should be able to make a prediction. So given an observation of the classes, should tell me whether this is a cat or a dog or whatever, should predict the class. This is what supervised learning is supposed to be. Okay, in traditional machine learning, the object, X, is described by some feature, and somehow we have a function, which is the feature extraction. So we describe the object X, let's say the image, with all these pixels, by some typically higher level feature. So from, and this is what people was used to do before deep learning. I remember I was doing also some image recognition a long time ago, so we had an image, so we were using some super complicated algorithm to extract the silhouette of the person or whatever, measuring the size of this image, measuring the relative position, and using this number as a feature. So this is the low level. This is, let's say, in my example, the image. This is a more abstract description of the image. And this is what feature extraction in general is supposed to be. And okay, in traditional machine learning, once we have the higher level features, we use the data. So the supervised data. So this is the annotation, the class, cat or dog or whatever. And this is the description to learn a model. Deep learning, typically, is different because deep learning does not need a dedicated, a specialized feature extraction mechanism. So deep learning can train the model directly from the low level. These are just the pixel of my image. It's a matrix of number or whatever, and we don't need a description, a higher level description of the feature associated to this image. In this sense, I think you can already see that deep learning is typically less interpretable. So you don't have an information that can easily parsed by a human. But if your focus is on the prediction, this is very powerful because you can do that automatically. You don't need the feature extraction. You can directly use this data to learn to train a predictive model. And this is typically what deep learning is doing. So this is perfect. No, it's not perfect because to do that, in the feature extraction, there is some knowledge, some information. So if you don't do feature extraction, typically you need more data. So deep learning approaches are greedy with respect to data. They need typically lots of data. The knowledge I have in my old algorithm to extract the silhouette of my cat or pet or whatever was something. And as a result, less data are needed to train such a model based on higher level features. If you use low level features, typically you need more data. Okay, you can also do unsupervised learning. And sometimes you need to do unsupervised learning because annotating the data is very expensive in many different sense. And okay, if you don't have information about why is the class cat or dog in my stupid example, the only thing you can do is just merge together objects that are similar with respect to their features. So this is basically what unsupervised learning is expected to do. So there are many techniques. Once you have the features, they try to merge together, to cluster together the similar objects. Okay, you can do that in the field of the traditional machine learning, so you can extract some descriptive high-level feature and merge together cluster whose object have similar high-level features, or you can just ask your deep learning technique to do that. So the supervised approach was something like that. I start from the data, and the output maybe is a very compact information. It's cat and dog. But somehow you can also do the other way around and obtain this kind of architecture, which was very popular. And this is what they call the variational autoencoder, because you are like starting from the information, from the low level, encoding, and encoding is basically going to a smaller dimension. So if this is an image of, I don't know, 1,000,000,000 pixels, this is a small array of 5 numbers, which is an abstract description of the object. And then you can do also the other way around. So from the abstract description, you can go back to the image. And you can train simultaneously this model. The training of the supervised model was based on the goal of the training of this model was to maximize the predictive accuracy on the annotated data. Here we don't have annotated data, so what we can do is to minimize the distance between the original input and the reconstruction in output. So this is what variational autoencoder are doing. This is not a deep learning lecture, but okay, I have this. If you click on this, this is just another collab. I'm just executing. It's just to give you some feeling. This I didn't write about. This was made by my student, which is a deep learning guy, working in reinforcement learning. But this was just a super simple variational autoencoder. So was this architecture. And it was using just fashion data. This is an unsupervised data set with these images. And the thing is try to group together these images. But what the encoder is doing is start from the image. It do this abstract reconstruction. And from this abstract, it go back to the image. And you can already see the generative concept in the sense that I can bypass this part, and given something here, I can build a new image. Then here, my goal is to ideally build exactly the same image in input, which will be the result of a perfect learning, which is not my case. Now, okay, this is also just to give you the feeling that now there are very good libraries. Perhaps if you work in a field related to AI, you use things like TensorFlow or PyTorch. They are super good in the sense that you can do very powerful computation with very few lines of code. And I'm not, let's say, discussing the detail, but this is really very simple stuff. And let me show you this. I'm just telling the autoencoder. I take the first 5 images of the data set, do the encoding, so go there, but then do the decoding. And of course, the result is not going to be exactly the same image. But still, let me see. So you see, this is the original image, and this is the reconstruction. Which, okay, not sure how exciting is this result. Maybe I can show you more. Is clearly not perfect. In some cases, very bad. But it's really just to give you the flavor that with very few lines of code, of course, based on very sophisticated libraries, you can implement something like that. And I insist a little bit because also the large language models are basically a further sophistication of the variational autoencoder idea. So basically, large GPT and all the other models are doing something like that with text data. They are trained with a crazy amount of data, and this was possible because these are unsupervised techniques. So you don't need a person annotating some high-level feature from the different text. You just put the text. The system is training in this way because you don't need the ground truth, because the ground truth is the text itself, and you want to minimize the reconstruction error. This was a very powerful idea from my perspective, and this is the basis of the recent breakthrough of AI. Okay, still have a little time. I need to stop at 10 or 10. Okay, so I think I can close this part. Another important, let's say, dualism is supervised against unsupervised. And I think this is even more interesting from our probabilistic perspective. Another dualism is discriminative against generative. Typically, let's go back to the cat and dog. I have an observation, or I have my image, and I want to predict whether this is a cat or a dog. Okay? So, in a probabilistic sense, I want, okay, in a general sense, I want to implement a function which, given the observation x, tells me what is the prediction y. Okay? In a probabilistic sense, this is a conditional probability distribution, which is able to tell me the different posterior or conditional probability for the different outcomes of the class y, given the input observation of the feature x. So the discriminative approach for us, probabilistic people, is about learning a conditional probability. Okay? Generative approaches are different. In generative approaches, you want to learn is a joint model for the class, comma, the features, and not given the features. And this makes a lot of difference, because in a discriminative model, you can only do predictions, which is not bad. Many times, you really just want to do a prediction. But if you have a joint model, of course you can do prediction. You can do conditioning, is what we did in my 8-state notebook probability mass function. You just compute the conditional probability by doing conditioning. But maybe you are not only interested in the probability of the class given the feature. Maybe you want to do what people call reasoning. And so you want to invert your scheme. And so you want to explain the prediction and to compute. If I know that the output is or should be y, so if I know that this is a cat, which is the most likely state of the feature giving you cat? You see? So this is what we call reasoning. You can do reasoning in a generative setting. You cannot do reasoning in a discriminative setting. So we should say that generative is better. Somehow, yes, generative is more general, because from a generative you can obtain this discriminative. But again, there is not a free lunch. To learn a generative model, you typically need more data. So if I'm going to talk later about Bayesian networks, credal networks. If I learn a Bayesian network from my data and I use them for prediction, and if I learn a neural network which is intrinsically discriminative, probably my neural network is going to perform better, because with the same amount of data, you have a more specialized model, and generally is going to be more accurate model. So this is somehow the situation. Okay, and the term generative AI is very popular nowadays. All the big achievements are generative AI, and this is definitely true. These are definitely generative models, but are generative models, based on this kind of idea. So there is no annotation. So what I wanted to emphasize is that when you talk, when press is talking about generative AI, is still referred to unsupervised settings. Typically, if you think GPT is generative AI, but is purely unsupervised. Somehow, okay, then the sophistication use also expert feedback and whatever. The traditional model where generative in, let's say, I would say is a deeper and more genuine sense, in the sense that the traditional probabilistic approach is interested in learning this joint distribution, which is a pure generative model, and which allow you to do also this reasoning. And this reasoning has to do also with explanation of your results. You will see that this kind of generative models are more explainable, but typically less accurate. So there is a kind of trade-off. Just to conclude this slot, I hope that you got this. No, but it's not really just my idea that deep learning is not all AI is about. It's a subset. It's a part of very important, clearly, which is itself part of the machine learning. So machine learning is not just deep learning, and still people use traditional machine learning in some cases, and still people need traditional AI, and sometimes the term is GoFi, good old, which is a bit sad in this sense, but the GoFi was the good old-fashioned, typically symbolic AI, which is still relevant also in the deep learning ages, while generative AI somehow is inside deep learning, is an application of deep learning. At least this is my abstract view. Okay, this maybe I can, not skipping, but just very quickly telling you that okay, deep learning is super effective, but we see limitation. And what I like very much this kind of, so this guy is a guy in probabilistic modeling, and he wrote this white paper about, okay, commenting the success of deep learning, which was amazing, but was especially related to computer vision, now natural language processing, and I would say natural language understanding. And from a very abstract perspective, it's like to say that, okay, what we call computer vision is a human faculty which consists in, is a function that given an image, given something, extract some value which is the meaning of the image, the content of the image. And we realize that what our brain is doing is corresponds to a function, and we realize that it's not too crazy to have a good approximation of this function. Neural networks are very powerful approximators. You can prove that they are universal approximators, so they can approximate any signal, what Bayesian networks cannot do. Of course, they need data for that. What we realized in the last 10, 15 years is that the amount of data we can collect is sufficient to have a very good approximation of the vision function for many applications. We are realizing that the same is true for what we call natural language. So natural language is something which is complicated, but from this approximating function perspective, not so crazy. And the data we have are good to obtain some very good approximation, which is what we call GPT-4. But this is really not about the meaning. It's just obtaining a good approximation of a function based on the correlation between the features and the class. So it's very good, but we should be more ambitious. This is basically the point, which is the point I like more, and this is also related to the causal analysis. This will be also considered in the last module. Okay, some people is proposing some, let's say, unifying approach between the neural approach, and the neural approach is low level. Like in computer vision, I have this sensing part, and this is the neural part, but I also need the brain to give some meaning to. So the idea, this is a very interesting, relatively popular paradigm by IBM people about merging the neural part and the symbolic part in a coherent framework. What causality is doing is also in the same spirit. So somehow we have to find a compromise between symbolic AI and deep learning to have better models. Ideally, this will give, I don't know if you never have the artificial general intelligence, strong artificial intelligence. These are people saying, this, for instance, if you link, this also link, there is a YouTube interview of a former colleague of us, which now is in DeepMind, is a very influential guy, is sure that by almost 2028 we will have general artificial intelligence, which means that is like exponential growth of these community of these technologies, because they can automatically improve the performance. So everything will be solved in 4 years. Not everybody is so enthusiastic and so optimistic. I don't know where what is going to happen, but just wanted to send, and I'm stopping for the break, that deep learning is clearly not enough. So we need to merge this very powerful technology with something on a higher level, something symbolic, and these graphical models I'm going to mention in the last 3 hours is somehow in this spirit. Okay. That's it. I think that we should take a break, and then we move to the third unit. Okay, so first lot, we did it somehow, no? And now, let's move here. This P means precise, okay, because of course the next, the fourth unit will be about imprecise probabilistic graphical models. Basically, probabilistic graphical models are probabilistic models. The meaning of the graphs is somehow overestimated. So the graphs is just a compact way to say something, and this something has to do with independence and with the composition, but let's be more explicit on this. So let's say what we are interested, let's say that now I decided that we are interested in assessing generative models. So what we want to learn in a probabilistic setting is a joint probability mass function. We are still precise. A joint probability mass function over the variables involved in my problem, in my system, in my world, whatever. So I have this x1, xn. Sometimes I use the bold for the joint variable, and I want to assess this variable. Okay, let's say, for instance, I'm interested in a model based on expert knowledge, so I could ask my expert to assess these probabilities, to assess the model. This might be complicated for various reasons, and the first and most important reason is that the number of joint state increase exponentially with, let's say we are in a finite setting, increase exponentially with the number of variables. Let's say these are Boolean variables. Okay, maybe I can ask my doctor to assess the probability of, the joint probability of treatment and recovery for the 4 different states. Treatment, yes or no, recovery, yes or not. But let's say that if I have 10 different Boolean variables, I cannot really ask my expert to assess these 1,024 joint states. And this is also related to the way our brain works. There are studies about the issues of human experts in assessing joint probabilities. For a human, it's much more natural to assess a conditional probability. It can be difficult to say. The probability of a person being recovered and treated is this. It doesn't work. Typically, it can be much more natural to ask, which is the probability of recovery given the treatment? Conditional probabilities are typically easier to assess. So there are problems if you wanted to directly assess this probability. But of course, it's clear that the major problem is the number of joint states, which is exponential. And okay, you can say, I have data. I can learn from data. But again, if you work jointly, in principle, you can assess. If you have a table with data about these 9 variables, of course, you can use any statistical learning techniques to assess a joint probability mass function. But again, if you don't have a crazy amount of data, very likely not all the outcome will be well represented. And so the way you learn this data can be very unreliable. So this can be an issue. This is an issue faced by people, especially in AI, learning models. And so a typical solution, and a very powerful idea, consists in decomposing the model. So instead of learning a joint probability, in this example jointly over the 9 variable, we learn different model. We decompose the joint model into smaller model involving a smaller number of variables. And let's say that assessing these smaller models is easier than directly assessing the joint model. But because of this decomposition property, assessing separately this small model is equivalent to assess a joint model. And this is really what the graphical models are about. Graphical models are basically decomposable models. And they allow to learn a joint, in this case probability, distribution by smaller pieces of information composed somehow. I'm very abstract. What is the meaning of these decomposition operators? Okay, it depends on the setup. I will be more explicit. But the general idea is to define a joint model by decomposition, and in this way to reduce the assessment of the joint model to assessing smaller model, where smaller means involving fewer variables. This is the general idea. The key to obtain this decomposition is independence. So let's say something. I know you already discussed independence, so let me just say something very, very quickly. Okay. If we have a joint distribution over my 2 variables, we intend independence as a factorization. So the joint must function factorized in the product of the 2. So the operator, the decomposition operator is basically the multiplication. You see? An equivalent formulation is in terms of irrelevance. So to say that x and y are independent means basically that the marginal distribution, or x1 and x2 are independent, the marginal distribution, the product of the marginal is equal to the joint. Equivalently, you can say that they are independent if and only if they are irrelevant. I'm not considering zero probability cases. I'm making things very simple, and basically the conditional probability of one variable given the other is equivalent to the marginal. So basically it means that x2 is not telling me something more about x1. It's just the marginal distribution over x1. This is what we call irrelevance. In the first line, this is what we call independence, but the two concepts are equivalent in this setup. Okay, and this is just a very simple algebra. And you can see also that independence is clearly symmetric. Irrelevance is symmetric because it's equivalent to independence. Independence is symmetric. Okay, you will see, or perhaps you already mentioned something about the fact that these concepts have been generalized to imprecise approaches, and in imprecise approaches things are not that straightforward. Basically the point is that every time in the imprecise setting, when we have a denominator, in the precise setting this denominator is a number, so there is a kind of proportionality relation. But in the precise setting, this guy might take different values. And so this kind of relation are different. So we will be more explicit later. And okay, let's take the irrelevance concept. We can say that if a particular variable is irrelevant for the remaining variables, this is clearly a decomposition. So this is good. But maybe is not something realistic. What I want to say is that if this variable is not relevant, I can just ignore. I don't need the decomposition. I can just remove it. So the real concept, the powerful concept for us is conditional independence or conditional irrelevance. So the useful decomposition we might have is when, for instance, given x3, x1 and x2 are independent. And this means that basically, given x3, the probability of x1 given x3 times the probability of x2 given x3 is the probability of x1, x2, everything given x3. So this is just a conditional version of independence. And this is something making things really useful, because it doesn't mean that x3 is not important for our system. x3 is important, but if we know x3, the relation between x1 and x2 disappeared. They became independent. And of course, this can be seen also in terms of conditional irrelevance. So if I know x3, x2 is not telling me nothing interesting about x1. You see? So this is the key concept for the kind of decomposition we want in graphical models. So let's say that what graphs are about. Graphs are really just a model of independence relations. It's just a qualitative and compact way to express a set of conditional independence relations to our model. Let's say this is my system over 9 variables. These are the 9 variables of interest, and I set a one-to-one correspondence between these variables and the nodes of a graph. There are graphical models based on directed graph and on undirected graphs. In the directed case, okay, I have this kind of arcs without arrows. And what is that? I need a semantic. In a very high-level sense, the semantic is separation. So the physical separation induced by a set of nodes between two sets of nodes correspond to the conditional independence. The graphs are maps of independence. In this example, I want to tell you that x4 and x5 are separating the green variables from the blue variables. So you see, if you are in a blue variable and you want to go to a green variable, you need to go through a red variable. And this is the conditional independence concept. Given x4 and x5, the blue variables and the green variables are independent, so they factorize. This is the semantic. It could be defined in a better way, but just to give you the intuition for undirected graph. For directed graph, we use what we call the Markov condition. And the Markov condition is just a semantic for directed graph. Maybe it's a bit more involved, but not so crazy. Every variable, and I'm focusing on the blue variable x6, is conditionally independent of the non-descendants, non-parents. So we have this idea of a variable. The parents are the immediate predecessors of the variable. The ancestors are the parents of the parents of the parents, and so on. These are the children. And the descendants are the children of the children of the children, and so on, recursively. So my variable x6 is independent of the non-descendants, non-parents. So for instance, x7 is not a descendant and is not a parent. x2 is not a parent and is not a descendant. You see? So what I want to tell you is that given the parents, given x4 and x5, this variable is, for instance, conditionally independent of x7. Why? Because x7 is not a descendant of x6 and is not a parent. x3 is independent because is not a parent, is not a descendant. So you see. x8 is, I cannot say that x8 is independent of x6 given x4 and x5 because it's a descendant, it's not a non-descendant. You see, look, quite involved, but it's not really so crazy definition. And this is applied separately to each variable. So in this sense, the directed graph is a compact way to express a lot of conditional independence relations according to these semantics, which is the Markov condition. Okay? This is the key to define a joint model in a decomposable way. So to define a joint model that for us means a joint probability over x1, x9, x2, x3, x9 in terms of smaller pieces of probabilistic information. Let's start from what people call the chain rule. Let's say that I want to assess the probability of x1, x2, x3, joint probability. By the simple definition of conditional probability, This guy is the probability of x1 given x2, x3, given the probability of x2, x3. If you move the probability of x2, x3 to the denominator, this is just the definition of conditional probability. Okay? So the first step is, okay, this guy is the product of these two guys. And then what we call chain rule is just doing that iteratively. So now this joint probability of x2, x3 is the probability of x2 given x3 times the probability of x3. So you see, given an ordering between your variables, you can also define something like that. Is this your decomposition? Somehow yes. But, okay, the first term, you can do that also for the joint probability between x1, x9, x1, and xn. But the first term is going to include all the variables. So it's not really a decomposition into, it's a decomposition, but it's not a decomposition into smaller terms. The decomposition in smaller terms appear when you have some irrelevance relation. Say, for instance, that given x2, x3 is irrelevant for x1. This is not written here. It's something we know. We know that for some reason, given x2 makes x3 irrelevant for x1. So basically means that in this term, we can remove x3. And we can just write x1, x2. And this is a more compact specification, because now we have the composition into 3 terms, and these terms, they include only 2 variables. There is no term with 3 variables. It's not a strong decomposition, but with larger model, by doing something like that, you can obtain something compact and define a joint model in terms of smaller, significantly smaller pieces of information. You see the idea? Now, let's say that we have a graph, and this graph should be acyclic. Otherwise, you will get, there are also some extensions to cyclic case, but you may get some contradiction. Let's say that we have a topological order. So basically, they are ordered in such a way that there are non-descendants after the order. So, for instance, you see these variables are in topological order. And if you are in topological order, you can just apply the chain rule iteratively. But then you can apply this kind of reduction. So the irrelevance, in this irrelevance, basically the parents, once you know the parents, all the other variables are predecessors, and so they became irrelevant. So, in principle, you will have the probability of x1 given x2, x3, x4. Let's take the example with 9 variables. x1, x2, x3, x9 will be x1 given x2, x3 till x9. But none of them is a predecessor. So you have only one variable. And then, basically, what I want to tell you is that in this way, the decomposition, because of the decomposition, the only variables you will see here are going to be the parents of your variable. These PR of xi are the parents of xi. And this is the kind of decomposition you have in Bayesian networks. So this is basically what we call a Bayesian network. So the idea of a Bayesian network is to define a joint model by means of conditional models. And these conditional models are conditional models for the single variables, conditional on the parents. The parents are the predecessor according to the graph. You can do that if you accept the Markov condition. So if you assume that the graph of your variables are describing conditional independence according to the Markov condition. So this, I would say, is a very powerful idea. Okay, this was in our example, this basically was just to say that the only irrelevance is here, and this irrelevance is telling me that x3 is not affecting x1 given x2, and basically in the graph, in the language of graph, means that the only parent of x3 is x2. You see? And to specify a Bayesian network, you need the conditional probability for each variable given the parents. So for x3, given the parent, which is x2. For x2, given the parent, which is x1. For x1, given the parents. There are no parents. This is unconditional. This is the idea. This is the larger example. So you see, now I have a distribution over 9 variables, which is decomposed in a product of conditional probabilities. How many? 9, one for each variable, given what? Given the parents of the variable. And this basically means, let's say that we still want to ask an expert. We don't need to ask the expert about the joint probability. I need to ask my expert about the probability of x1 given nothing, so the marginal probability. I have to ask the expert about the probability of x2 given x1, and so on. And this is easier because it's more compact and because it's conditional probability. Please. I'm sorry, it's a single factorization, you mean? Sorry, you're right. It's a typo. Sorry, it's x6. Good, you got it. I did. Yeah. Sorry. So I should fix. Let me fix now, otherwise I will. No, then I have to upload. Thank you. Sorry. Now here we are. X9 given x6, x7. Okay. So this is the Bayesian network idea in a super nutshell. Let me just show you a notebook. And for this notebook, for this notebook, just to make my life a bit easier, I'm using a software, but this is a Bayesian network library in Python, which is called the PyAgrum, which in turn is using a C++ library for graphical models. And my experience, if you cope with small models, this is very good. This is very good. If you need more complicated application, maybe it's not best, but for this setups is very good. And you know, if you're using Colab or something, you probably need to install it. Okay, just let me show you. Okay, this is basically what one would expect from a library. So this is just, let's say that we wanted to create a Bayesian network from scratch. First step, the variables. The variables are the basic ingredient, no? And let's say here I have 3 variables. Okay, this is a description. This is the name of the variable. No, this is the label of the variable. This is the name. And this is the number of states. So I just have 3 Boolean variables. First step. Second step, the graph. And the graph basically is by saying that x1 is a parent of x2 and x2 is a parent of x3. This is a chain graph, but it could be any. Okay. Then, okay, I think PyAgrum is very good for visualization. They are very good visualization setup. And this is the qualitative part. This is the graph and the variables. Now, let's be quantitative, and let me define what I call the conditional probability table. Okay. For x1, I don't have parents. So this x1 given nothing. So I call it conditional, but in practice it's unconditional. It's the marginal probability for x1. And let's say that my expert or my data are telling me that this distribution is 0.4, 0.6. And the CPT is a conditional probability table, even if in this case is unconditional. And this is the model for x1. Next, I need to define. Please, you have a question? I need to define the model for x2 given x1, given the parent. And this is the second conditional probability table. And this basically means that the probability for x2 if x1 is 0 is 1. Okay, maybe 1, 0 is 2, is determined, let's say 0.99. Well, whatever, it's not important, it's just an example. So this is the distribution for x2 given that x1 is 0, 0.99, 0.01, which is this guy, and if x1, which is the parent, is 1, is 0.9, 0.1. I think in my slides I'm calling these guys the columns of the CPT because I'm used to work like that. Here are the rows, but basically the conditional probability tables is made of conditional probability mass function, one for each value of the parents. So here we have 2 because the joint value of the parents is a single parent, and we have 2 states. You see? Here, for this guy, we have 2 parents, and let's say everything is Boolean, so we have 4 different joint value of the parents. So the conditional probability table will be probability for x6 given the 4 possible value of x4 and x5. So it will be a table of 4 columns or rows, depending on the way you sort them. Okay, let me be back. So, and let's say this is the other CPT, conditional probability table, for x3 given x2. And once I'm done, this is my well-defined Bayesian network. What can we do with the Bayesian network? Okay. Credal networks are exactly the same with a small a star, and the star is telling you that instead of probability mass function, we have imprecise models, so sets of probability mass function. That's why I'm spending so much time for Bayesian network, but I think it makes sense. So what can we do with the Bayesian network? We want to do inference. So this is a specification, a compact specification of the joint model. And once we have the joint model, we can interact with the model and extract new information. This is basically what AI is supposed to be. Once you have a model specification, you do inference. So you extract information that is new for you, is of interest. The most simple, maybe somehow most simple, even if it will not be always that simple, inference task, is to marginalize knowledge. So I have my distribution over 9 variables, but I'm interested on the marginal probability for x5. And this is called the marginalization. And you see, here the product over all the variables of the conditional probability for the x given the parents, this is just the joint. This is the joint distribution. This is this guy, the product. And for marginalization, I have to sum out all the variables apart from the ones of interest. So here, I'm summing out all the variables apart from the queried variable. So you see, is a sum over a productory, a product. And you have to compute this guy. So for instance, you have to compute the marginal for x5. This is an inference problem. Another inference problem is updating. So I might be interested in, so let's say that I'm still interested in x5, but not in a marginal sense. I'm interested in x5 given the value of x1, given some particular value of x1 and x8. So this is what I call evidence. And I do an updating, so I compute the posterior probability for the variable of interest given this new information. This is a conditional probability, so the object to compute is a denominator. This, if you can see, is the probability for xq and xc, because again, is the product, so is the joint, but now the sum is not only over xq, is not only over all the variables apart from xq, is over all the variables apart from xq and xc. So this is p of xq, comma, xc. For a conditional, should be divided by the probability of the evidence, xc. And now here the sum is like, sorry, this another typo, was xe. Sorry. It's not bold-faced, but okay. Because this should be the probability of the evidence, to have a conditional probability. Okay, these are two different tasks, but if you want, basically this is a marginal probability and this is a marginal probability. So if you can compute, if you have an algorithm to solve marginalization, you can also compute a posterior. As said, in imprecise probability is not like that. An imprecise probability is more complicated because basically this is just you can see that this is like a normalizing constant, but with imprecise probability this is not constant. So, but okay, basically marginalization and updating are basically the same problem. They are NPR. Maybe you have not. Some of you, yes, but you are not all computer scientists. It's just to say that there is not always a fast solution for this model. And basically this means that if your model includes many variables, the exact computation of this algorithm can take exponential time. So it can be too slow. There are very good approximation schemes for Bayesian networks. So Bayesian networks are NP-hard problems. This kind of inference is hard. But let's say if for your task you can tolerate some approximation, I think this is not a big problem. So, an even more challenging problem is the map inference. This will be marginal maximum a posteriori, but you can also call it the most probable explanation. And this is what I was calling also reasoning. Because here is like to say that, okay, I'm interested in finding the most probable state of a variable, or typically of a set of variables, given some evidence. I know that my patient has this symptom, has this story or whatever, which is the most probable configuration of some other variables. Is a bit more involved inference task, and it's also more complicated from a computer science complexity theory perspective. So if this NP this is NP-PP, but basically it means that in general there is not an exact fast algorithm, and it's even more complicated than this one. So these are just the typical inference. If you have a problem, you use a probabilistic approach, so maybe you can consider to use a Bayesian network, and the answer you want to obtain about your system can be typically reduced to this kind of problems. And the libraries for inference libraries for Bayesian network are solving this kind of task, typically. Just very quickly on the notebook. On this notebook, the first part was the model specification. This was marginalization. So here I'm just computing the marginal probability for x3, which is 79 and something % for the first state and the complement for the second state. Here I'm computing. Here is just these are all the marginal distribution. So this is the marginal probability for x1, this is the marginal probability for x2, this is the marginal probability for x3. You can observe that the marginal probability for x1 is 0.4, 0.6. So this was computed by the inference of this library. But this is a trivial inference because it's something we already specified. We don't need any additional computation. While, for instance, to compute the marginal for x2, I need to compute... If I'm interested in this guy, I need to compute sum over x1. And this is the CPT. This is an CPT. But you see, this is a new computation. So this is a new piece of information. And what these libraries are doing is basically something like this computation. Typically, the library tries to mix the sums and the product. So to move the sum inside the product. Because In this way, you do less computation. If you first compute the product and then you do the sum, you're doing like a brute force computation, which can be okay with small model, but with larger model would be clearly exponential and at some point unfeasible. Okay? So this was about probabilistic inference with Bayesian network. Okay, I just wanted to mention, and I want to mention that because also the spoiler is that we are going to consider an imprecise probabilistic version of these guys, which is called the credal instead of Bayesian network. Another popular class of models are the so-called, in general, circuits. Sometimes they call them tractable model. More specific, this class of model is called the sum product network. They are still considered the graphical models. And okay, the story of this kind of models is that, this is my version of the story, at some point deep learning was clearly beating Bayesian network and other approaches. So the performance of neural network in terms of accuracy was much better than the performance of Bayesian network. And you see, it is a trade-off between Bayesian networks are more explainable, but less accurate. Neural networks are more accurate, but less explainable. And so people from my community started to think, what can we do to compete with neural networks? And they started to create deep graphical models with many layers. And some of the proposals were something like that. Okay, let me first explain you how it works. So this is a graph. In this case, the graph is not a semantic related to the independence. The graph is just showing you, is a computational model. It's just showing you how you do the computation. And let's start from this part, even more. Let's start from this guy, this slice of model. So these are the two states, and we annotate the arcs with probability. The probability for this guy is 0, 1. I don't have a space to put a lot of number. When the arc is dashed, it's just the complement. So this is 0.1, this is 0.9. And this is a model of a single probability mass function. Let's say that E is the indicator function. So it's 0.1 for the first state of x1 plus 0.9 for the second state. So it's just a distribution over x1, 0.1, 0.9. You see, this is a single PMF. This guy is another PMF, is 0.2, 0.8. And these nodes are basically indicators. The arcs are annotated by probability, and these are sum nodes, because I'm just taking the sum of the two indicators weighted by the probabilities. And this is a way to encode the probability mass function. I can do the same here for x2. So you see, this is 0.5 first state of x2 plus the complement 0.5 second state of x2. Here I have 0.3 first state plus complement 0.7 of the second state. Okay? And now I have 4 probability mass function, 2 over x1 and 2 over x2. Now I move up, and these are the product nodes. The product nodes don't need any probability on the edges because we are just taking the product. So you see, there is an independence concept, but it's inside the model and is not described. It's described by the graph, but it's just described by the product node. And I'm taking the product of this distribution here and this distribution. So in this product node, I have this product. In this product node, I have this guy with x1 times this guy for x2, and here I have this product. And everything then is done recursively, moving up. So on the top, I have a sum node, and I take the weighted sum of 0.5, this product node, which was this distribution, joint, then 0.2 for this guy, and then 0.3 for this guy. So again, I'm encoding in a compact, but maybe you already can see is typically less compact way, a joint probability mass function. So this is still a joint probabilistic model. if you want, this is considered less interpretable, because the graph is not a model of independence, it's not a model of the correlation between the different variables. It's just a model of the computation. This is a disadvantage. The good news with respect to Bayesian network is that inference here is basically achieved by propagating through the circuit, through the graph. So inference in this kind of model is typically linear with respect to the graph, which is the circuit. So basically means that the time you need to compute the inference is proportional to the size of your circuit, your graph. And that's why this model typically depends also on the inference task. And for this reason, these models are called also tractable. This is an example of trapped. But there is a kind of trade-off between tractability and explainability. So neural networks are very tractable but very unexplainable. Bayesian networks are very explainable but very untractable. This is somewhere in between. And in fact, this model, they can compete against the deep learning model. Bayesian networks are less accurate. They have other advantages, but they are less accurate, typically. Okay. Now I will start to move to the imprecise probability extension of these ideas. And this is a kind of short story of these graphical models, including also the imprecise probability versions. So this was a long time ago, the first book formalizing all the idea on Bayesian networks. And the guy who invented them is Judy Appel. Judy Appel is a super important guy for computer science, at least for symbolic computer science. He's very much against the deep learning hype, because he was always interested in symbolic method, and more recently is interested in causal technique. Not only more, he was always interested in causal techniques. But it started from Bayesian networks, and Bayesian networks are not causal models. Remember that the semantics of the graph is a conditional independence. So the graph is telling you about the correlation or non-correlation between your variable. The graph has not necessarily a causal meaning. These are pure probabilistic models. Judy Appel was one of the persons who started to work on this stuff, and then he did an evolution of this model in the direction of causal models. But at some point, not sure you touched the story of the imprecise probability community, and also there are other communities with maybe between 90s, late 90s, something like that. They started, this may be a too simplistic description of what happened, but at some point people was not, let's say, satisfied by traditional probabilistic approaches. For instance, at that time, these models were used to express knowledge. Expert systems were based a lot on Bayesian networks. But at some point, people realized that standard classical probability mass function are not enough to capture the knowledge of your expert, to express human knowledge, to provide a good elicitation of the human knowledge. And so they tried to extend this model, and imprecise probability was one of the formalism. From our point of view, the most general, the most beautiful one. There are also there have been other proposals, especially in these during these times, and these ideas have been applied to graphical models. And credal networks is basically the topic of the next module, and is just an extension of this idea to imprecise probabilistic approaches. Then people working with graphical models with classical precise moved away. What is very nice from my perspective is that very recently we realized a strong relation between credal networks and causal models, basically. From some point of view, there is a kind of equivalence between. So I'm going to show you that in machine learning, imprecise probability are important if you have missing data, if you have a few data, Imprecise probability are important if you want to implement a knowledge-based system and your expert is not able to assess a single probability. You use natural language and you want to translate this natural language into some quantitative model. So maybe you can use an interval of probability, whatever. But in the case of causal model, the connection is even stronger. Basically, you need sets of distribution because of the structural nature of this causal system. Because of the presence of hidden variables in the causal models. So basically, I'm going to talk you about credal networks now. I start now, then we take a break, then I go on. And in the afternoon, I will move to causal models. But in a sense, they are the same topic. Okay, let me breathe. And now we can move to credal networks. So what are credal networks? Bayesian networks with set-valued parameters, with imprecise parameters, with credal sets instead of probability mass function. Okay, so this is the extension we want to do. As usual, just before starting, I need one slide to define a bit of notation, and also, from my perspective, to define some important concept. Okay, what is a credal set? From, if we want to be very general, it's just a set of probability mass function. Precise model is a single probability mass function. Imprecise model is a set of probability mass function, of course, all over the same variables. I'm generally using this K. Okay, whatever. Once I have this imprecise knowledge, I'm interested in computing expectation. There is a function of my variable telling me something of interest. Either I would like to compute the value of this function for this on the actual state of this variable, but I'm uncertain. I don't know the state of the variable. I said that I want to compute the expected value of this function, but now there is an additional level, because this expectation is based on the probability mass function. If I have a set of probability mass function, I will have a set of different value for the expected value of my function. Which one is better? I don't know. Imprecise probability models are not hierarchical models, so there is not a probability over the element of my credal set. My model is intrinsically set valued. So the only thing I can do is just characterize my expectation in terms of bounds. I can compute the lower and the upper bound of my expectation when P varies in the credal set. Which one is the most representative value? The lower bound, the upper bound, the midpoint? I have no idea. There is no second order knowledge. So the interval will be the result of my inference. Okay, this is going to be my optimization task all the time when I do this kind of models. Okay, let's say that I work in a finite setting. Basically, this expectation, which is a linear functional, is not affected by the convexification. I might have a set of probability mass function. If I take the convex closure, the convex hull of this point, I obtain a convex set. If I replace K with the convex hull of K, the lower bound and the upper bound of my expectation will remain the same. So nothing changes if I do convexification. But if I do convexification, basically, this is, I don't know, some of you who is familiar with linear programming. Linear programming is a kind of optimization, constrained optimization. Somehow is the simplest optimization. And it's about optimizing a linear function with respect to these are the optimization variable, which are free to vary in a region. But this region, let's say in a finite setting, is defined by linear constraint. This basically will be a polytope in the probability simplex. So these are linear constraints on P. This is a linear function of P. This is what we call linear programming. The solution of a linear programming is in this finite setting on one of the extreme points of this region. And this basically means that this is an optimization on a continuous domain, but you can equivalently consider this continuous optimization as a discrete optimization by considering only the extreme point of the convexification of your credal set. Stupid visual example. This line is the probability simplex. So for a probability mass function over two variables, over a Boolean variable. Any distribution, 0.1, 0.9, 0.2, 0.8, 0, 1, 1, 0, 0.5, 0.5, they lie on this segment. Okay. Here, my credal set is made of three distributions. 1, 2, 3. These 3 points. What I'm telling you is that if I compute any function, the expected value of any function of this P of x, when P of x has one of these 3 values, the bounds can be equivalently obtained by considering the convex closure. 3 disconnected points are not convex. Their convex closure is this segment, you see? And this is this optimization on the convex hull. But this optimization is equivalent to the discrete optimization obtained by considering only the extreme point. And the extreme point of these two. So I start from this guy, I convexify, and I take the extreme point. And the solution is always the same. You can prove that in the finite setting. And this basically means that the kind of inference we are going to address will be, first of all, it means that generally we consider our credal set convex or convexified. And we assume that the number of, we typically assume, and this is okay for many applications, the number of extreme points they have is finite. It's not always the case. You can easily imagine some situation where the number of extreme points is infinite. For instance, I work also with expert system. Sometimes there are synergetic effect when one variable and another variable, they work together to increase something on the child variable, and this is a quadratic constraint. But very often you have linear constraints, and with linear constraints you have basically a polytope, which means a finite number of extreme points. Okay? Okay. Please. Sorry. Yeah, let's say, if your perspective, which is in this case my perspective, is the one of inference, you can consider this an equivalence relation. So this credal set is equivalent to a credal set, and I will say that there is an equivalence class, and the representative element for me, and I'm interested in combinatorial approaches, is made by the set of the extreme points after convexification. Not for expected value. For other tasks, I think you can find a situation where the two tasks have different answers. No? And also there is something, because here I'm not considered, okay, in a sense, this kind of inverse are not affected. This is the convex closure, so they are closed. For instance, when you do inference with these sets of desirable gambles, when you can remove a part of the, and I think, I'm not an expert, but credal sets are not general enough to describe some situation with sets of desirable gambles. So you need these are more sophisticated models which can distinguish also this kind of situation. But for the kind of inference which are interested in, which are typically computing conditional, posterior, lower, upper conditional probability or marginal probabilities, this is general enough. Sufficiently general. Okay. This one step, 5 minutes, just I will not finish, but we'll finish with the definition of credal network after the break, but I need one more concept, because credal networks want to extend the Bayesian networks, and Bayesian networks are based on the notion of independence. We need a notion of independence for credal sets. You already discussed that, but let me say that, okay, if I have a joint probability over x and y, I can say whether x and y are independent or whether y is irrelevant for x, whatever. If I have a credal set, a joint credal set over x and y, what does it mean that x and y are independent? You know, there are different ways to characterize independence and irrelevance with imprecise probabilistic model. I will say that the most natural one, what I'm doing here, is very naive. It's kind of sensitivity analysis, kind of perturbation. Instead of a single distribution, I have a set of distribution. So the most obvious option would be just to say that, okay, independence means independence on each point of the credal set. And it was some people call strict independence. I don't know whether they are, sorry? Complete, sorry. A complete independence, which is very natural, but is not exactly what I'm going to use. For the simple reason that this definition clashes a little bit with the convexity. I'm almost done, but let me present you. Let's do like that. No, you have to take the break, and this is the very important toilet break. but during the toilet break, try to imagine this. So let's say x1, x2 are Boolean. Okay, if x1 and x2 are Boolean, the joint variable x1, x2 has 4 possible states. Okay. A probability mass function of these 4 states is made of 4 numbers. But the last number, for instance, is 1 minus the sum of the first 3 because of normalization. So let's say basically we have 3 parameters. And that's why you can represent this guy, a probability of x1, x2, which is, if you want, is a quaternary variable. You can represent as a point in the 3-dimensional space. For instance, this is false, false, true, false, false, true, the first 3 states, or whatever. So you can represent it in a 3-dimensional space, and you can consider, the probability simplex. The probability simplex is the set of all the possible distribution. And the probability simplex, probably you saw something like that. But this was the simplex, which is a triangle. And the triangle is for a single ternary variable. So this is a ternary variable. What I already did here was for a binary variable. This is the simplex for a Boolean variable. For a quaternary variable, the simplex is a 3D volume. Okay? And basically you can shape it as a tetrahedron. Then I will show you in a better way. But you can shape it like that. But now this is not a triangle. This is the volume. And each point, for instance, this is 1, 0, 0, 0. And this is a distribution assigning all the probability mass to the first state of this fourth state. 1/4, 1/4, 1/4 correspond to 1/4, 1/4, 1/4, and the third one is not there because of normalization. This will be a uniform distribution. So try to imagine. Then I try to visualize, even if my 3D skills, even with computers, are not that good. And now imagine that the full volume of the tetrahedron include all the distribution. Some of them are independent. For some of them, it happens that P of x1, x2 is equal to P of x1 times P of x2. So inside this tetrahedron, there are some distributions satisfying this condition. This is going to be a surface inside the tetrahedron. I think it will be nice to visualize this, but we can do after the toilet break. Okay? No, let's brief a little bit. Okay. So you see the problem. Not sure whether was okay to find the surface of the independent. Say again, I forgot the. Complete, yes, which is a complete independence distribution inside the simplex, which is this tetrahedron. So now I really need your geometric imagination, because my plot is not that nice. But you should imagine this surface inside this tetrahedron. And all these points, the point of this surface, are independent distributions. So this is, for instance, in 3D is 1, 4, 1, 4, 1, 4. Remember, this is a distribution of a quaternary variable, but the last coordinate is not there because of normalization. The last coordinate will be 1 minus 1, 4, 1, 4, 1, 4, so it's 1, 4. So this will be a uniform distribution, and a uniform distribution can be intended as the product of two uniform probability of the Boolean. So first coin 1/2, 1/2, second coin 1/2, 1/2. Their product is 1, 4, 1, 4, 1, 4, 4, and is an independent point. For instance, also this extreme distribution 1, 0, 0, 0 is independent. So this will be another independent point. What is nice from my perspective of this distribution, of this surface, is that it is maximally non-convex. And what is not a formal definition, it's my definition, is just to say that if you take 2 points on this surface and you take the convex closure, and geometrically the convex closure is just the segment connecting the 2 points, the convex closure will be outside the surface. So basically, the convex combination of 2 points, or of 2 independent distribution, is not independent, which is kind of strange. But you can see, if you write this very abstract visualization of this concept, at least in general. And basically, it means that strict independence completing, sorry, I should write. My fault, because I used also this denomination. But complete independence is okay, but it somehow clashes with convexity. Why should we stick on the convexities? Is not such a problem. But for credal networks, I want I'm focused on inference, and why I want my inference to be a combinatorial task. So, sorry, I'm moving. Sorry. Just a second. Basically, I want to solve my inference in this way, as a combinatorial task. So for me, it's important, basically, to have a convexification, because I want to do my inference on the extreme point of the convexification. That's why I'm not using this notion, this very natural notion of strict independence, but the notion of independence I'm using is that of strong independence. A strong independence is basically the classical independence, what we call stochastic independence for precise probabilistic model, but on the extreme point of the convex closure. So this looks strange, because basically you have in the convexification you have points that they don't factorize, but the extreme point should factorize. So this is somehow the idea. Of course, let me tell you that this is not the only concept. You probably discussed the other. And among the other ones, the most important is clearly that of epistemic irrelevance. That basically means that the expectation, if x and y is irrelevant for x, basically means that the expectation, the lower expectation of any gamble, functional, whatever, are not affected by an observation on the other variables. But let me say that the original definition of independence, notion of independence, used for credal networks, so used to extend Bayesian networks, was that of strong independence. And I'm basically focused on strong independent credal networks. There is a lot of work especially everything, I think it's not everything, but the work of Jasper, I think, is very exhaustive in exploring the field of credal networks with epistemic irrelevance. And I think is very important piece of work. Here, I'm focusing on strong independence because my perspective, if you want, is more the perspective of a sensitivity analysis. So I have my distribution, but maybe this distribution are not exactly the ones, so I propagate them. So I'm considering also these models that are nearby in some sense. So let's formalize this notion of credal networks. Now we have all the ingredients. We have Bayesian networks. We have the conditional probability table of Bayesian networks, and these are made of probability mass function. We replace the probability mass functions with credal sets. That's it, somehow. So that's it. This will be Eric, sorry. No, the notion of independence, the complete. Not too late. Which is strict. I stop buzzing you. Okay, so this will be, let's say, a complete credal network, complete independent credal network. But in this way, we lose convexity, and I want convexity. So I'm not using this complete independence, I'm using strong independence. And strong independence basically means that I ask the factorization of the Bayesian network on the extreme point of the credal sets. But let me be more explicit. Oh, no, before being more explicit, I will say that there is a not obvious remark here. So if we go in this direction, basically, so if we define, we take a set of distribution. For each set of this, for each point of the distribution, you define a Bayesian network. For each Bayesian network, define a joint distribution. Then you take the and then you obtain the joint credal set. And you do convex closure, and you take the extreme points. You will need a characterization of the extreme points. And the very good news from my perspective is that the extreme point of the convexification of the strict model are combination of the extreme points of the credal sets. And these basically are included in this combination. So this, what I want to tell you is that basically if you work with stronger credal networks, you only have to consider the extreme point of the local model, of the decomposed model, take all the possible combination, and in this way you define a collection of joint probability mass function. But I should be more explicit. So let's start from scratch and see the ingredients to build a credal network. We have our variables. We have a graph, and as usual, we have the semantic of the graph, which is the Markov semantic. So basically, the graph describes conditional independence in the strong independence sense. Okay. Now, basically, if you now let's say that for each variable given the parents, a Bayesian network has a probability mass function, a credal network has a credal set. If you create a joint credal set by the joint distribution obtained as a Bayesian network, you will have the complete credal set. Then you take the convex hull, and I'm interested for inference reason, because I want to compute inferences, and I know that the inferences are on the extreme points of the convex closure of the credal set. I'm interested in the extreme points. And the extreme points are based on Bayesian network that are combination of the extreme points of the credal set, the local credal sets. And this, for me, is very good news. because basically means that when I want to compute an inference in my credal network, I need only to consider generally a finite number, exponentially high. This is a problem, but a different kind of problem. But I have a finite collection of Bayesian networks to consider as candidate. And the extreme points here are combination of the local, so the extreme points of the joint distribution are combination of the extreme points of the local credal sets. Of course, the number of combination is exponentially high, and this is related to the combinatorial exponential complexity of the inference with credal networks. But I have a characterization. So if you want as a brute force approach, I can compute inference in credal networks by only considering a finite number of Bayesian networks. So if you take this definition, which is based on the notion of strong independence, and if your local credal set have only a finite number of extreme points, sorry, you can say that a credal network is equivalent of a collection of Bayesian networks. Each Bayesian network defines a joint distribution. You can compute your inference on all these joint distribution and then take the lower and the upper bounds to characterize your credal network inference. This is the idea. This is very, very convenient from my perspective. So in this notebook linked here, I'm not using a library for credal networks. Pyagrum has some credal network feature, but very, very basic. I'm just doing brute force credal network inference. So if you see, I'm going a bit quickly, but now instead of a single probability mass function, I'm having these sets of probability mass function. Here I'm using only two for each conditional probability. And this is very bad if you are a software developer. But okay, it's very naive, but one reason is that I'm very bad with code, but the second reason is somehow on purpose to show you explicitly that I'm considering all the possible combination of the local credal set. I have two possible ways to specify this distribution. I have two possible ways to define this distribution. I have two because the credal set here has two vertices, but okay, it depends. Side remark, if you have a Boolean variable, in a Boolean variable, a credal set intended as a closed convex set of distribution cannot have more than two vertices. And this is very good for complexity, for inference. You remember this is the simplex. So this, for instance, is 0.5. 0.5 is a uniform distribution over a coin. This is 0.1, 0.9. Okay. A credal set would be any set inside this simplex. So this, let's say that something like that with no distribution inside. Something like that would be a very strange credal set. Let's say something like that. I have this and this. This will be a non-convex credal set. We should convexify, and convexify basically means to do that. And once you convexify, we are on a one-dimensional manifold, and we have only two extreme points. So this, I don't know, is 0.9, 0.1, whatever, this 0.9, 0.1, 0.9, or whatever. But what I want to tell you is that if your variable is Boolean, you cannot have more than two vertices. If your variable is ternary, you know this is the simplex. Let's say x equal to 0, x equal to 1. These are the three states. You might have a credal set with an arbitrary number of extreme points, a closed convex set with an arbitrary. From the point of view of inference in credal networks, the number of vertices matters a lot, and binary variables are better. Not surprisingly, there is one of the few exact algorithms for credal network, because the problem is NP-hard. So in general, you cannot have a fast exact algorithm. But there are fast exact algorithms for Boolean variables under some additional assumption. Why? The insight is that with Boolean variables, you only have two vertices to explore. But they are combined, so they can still grow up to an exponential number of joint combination. So this basically by building your credal network as a collection of Bayesian network with different specification in a brute force way. What about inference? Inference is exactly the same. So inference is inference with respect to this joint credal set. So again, a marginal query will be just to compute to marginalize the variable, and some of your colleagues told me maybe this was not. This is a set minus. So this is the whole set, removing from this set xq, which is the variable. So I sum out over all the variables apart from xq. So you see, inference is more complicated with credal network because we have the product to generate the joint distribution. Then we have the sums to sum out the variables which are not interested in. And then we have the optimization because we want to take the lower and the upper bound. In this case, for instance, the lower probability. You can do that in a brute force way. And I'm doing that in a brute force way in the notebook. So I compute, I compute all these guys. And for all these guys, I'm computing, here I'm computing a marginal. So I already screwed up my slides. Sorry, here we are. So this is a marginal query, and this will be a conditional or an updating task. So now I'm interested still in the probability of xq given some evidence. Again, it's a conditional probability, and so I have this conditional probability to consider. This is the conditional probability, and I have to take the minimum over all the possible specification of the extreme points of the credal sets. You see? This will come later. Wait a second. And what I'm trying to show in this, what I'm trying to show in the slides is basically computing all these conditionals. Basically, in this, I have two extreme points here, two extreme points. So I have 2 to the power of 1, 2, 3, 4, 5, which is 32 different Bayesian networks. For each one, I compute the conditional probability, and then I'm interested in the lower and the upper bounds. So this will be an array with 32 inferences, Bayesian network inferences, but the credal inference is just the lower and the upper bound, which are these two values. So this computation is basically, let me move away quickly. This computation is like, I do this computation 32 times, one for each specification of the local credal sets of the different variables for the different value of the parents, and then I take the minimum. This is brute force. Okay? If you want to do something smarter, basically you have to move the sum inside the product and ideally the minima inside this expression. So in this way, you reduce the number of basic operations required for this computation. But this cannot be done in general. The problem is NP-hard, and is even a higher class of complexity with respect to Bayesian. This is a generalization of Bayesian network inference, but is even harder. Okay? But I'll tell you that there are approximate schemes, I would say some of them good approximate schemes and libraries to do this kind of computation. Here, I want to do brute force to have you sing from very close what we are supposed to do. And if you remember, when I was mentioning these two problems for Bayesian networks, I was saying that they are almost the same. It's true that here we have the denominator, but this is like a normalizing constant for Bayesian networks. For credal networks, it's not anymore, because this is not constant, because we have different specification, different Bayesian networks, and the denominators will be different. A very appealing idea would be take this optimization separately on the numerator and the denominator. So to minimize, I could minimize the numerator and maximize the denominator, if I want to take here the minimum. But this is not exact. So this approach is going to give you more imprecision than what is needed. It's simpler, but you have a larger bound, a less informative bound, please. Sorry, my usual stupid error. Here should be apart from XQ and XE. Sorry. You can guess that I wrote this during the holiday. Should be this one. And then I will re-upload the right one I share with you. Is that? It's the same error, for sure. Because on this one, yeah. I will fix it. Sorry. Sorry. Of course, they are different. Okay. So let me just say something. So doing two independent please. Yeah. Independence concept. The complete is smaller. But the inference are the same. For basically this point, because this is still a credal. If the credal sets have only a finite number of points, which is very often the case, and basically this is the reason, because this would be the strict, then I take the convexification, then I take the extreme points, but the solution is the same. Mm-hmm. Yeah. So the final solution will always be part of the credal set will be larger, because this is making larger. Maybe your point is that these are just let's say we are doing this strict. So this is just the credal set of the strictly dependent joint distribution. We do convexification. When we do convexification, we increase the credal set. So for sure, this includes this. But the solution, if you take if you take the lower expectation of your function, the value is the same. You see? So the credal set is larger, but the solution is the same. Okay. Here I take the extreme points. So in a sense, this is larger than this one, because here I am removing the non-extreme points, but still the solution is the same. You see? And if you look up, you see this is the initial model. Then I do convex closure, and I get a larger model. And then I take the extreme points, and I end with 2. It's okay? Okay. So we discuss offline. Okay. Sorry for not being clear. Let's go back. So this for me is just an important, let's say, remark. And the notebook shows you how this happens in practice. So basically, here I'm again doing this very awful brute force computation. But now I'm separately computing the probability of the numerator and the probability of the denominator. And then I take the minimum of the numerator divided by the maximum of the denominator. And basically, you can see that what I get, sorry, no, to execute from scratch. But okay, basically the message for you is that in this way, if I do this separate optimization, I get an outer approximation. So I get a more imprecise inference. So this is based on the two independent optimization. So this will be the interval based on this approximation, which is simpler to compute, but the exact one is this one. And you can see is much more imprecise, much less informative. Let me come back. Just for your information, okay, this is a library for credal networks, which to me is good. It's very flexible. It's implemented by my group in Lugano. The point is in Java, which now is maybe for you is old-fashioned stuff. Is boring to install Java. It took to us a lot of time. Now we are happy with this library, but it's in Java. So it took years to have a good library. Now we want to implement in Python. We are working on it, but still we don't have a good Python porting. So if you want to use, you need, it's not crazy, there is documentation, but you need Java, which is very bad. It's our fault. And let me say that, okay, this implements exact inference, but exact inference is something you can do, as you can imagine, for very small network. And there are good approximate schemes. Not surprisingly, there are exact schemes for special models, like binary networks with a simple topology, white trees with epistemic irrelevance, no matter whether the variables are binary or not, and there are approximate scheme. This was an idea I worked on, which I think is at this moment the best approximation scheme we have, is basically to say, okay, I have to optimize, and in doing the optimization, all the credal set can vary. But let me fix all the credal set to a specific value apart from the ones of the credal set of a single variable. If you do the minimization only over the credal set of a single variable, this function is going to be a linear function, while in the general case is a multilinear, it's like a polynomial. So linear tasks are easy to solve by linear programming. And even if you want to compute the posterior, this is called the fractional linear programming. And in this way, you can obtain inner approximation. And you do that in an iterative scheme, and in this way, you can get very good bounds. So this is basically something you can do in practice if you have a large credal network. If you have a small credal network, if your extreme points are not so many, maybe you have chances also to compute some exact inference, but for sure not in the general case. Okay. Just to conclude the discussion about this imprecise, the theory of these imprecise probabilistic graphical models, also some product network. You remember this circuit idea? This circuit idea was also extended to credal sets. And in this case, it's even simpler because here the graph has not a independence semantic. There are independence relations, but they are implicit in the structure of the circuit. They are also called the context specific. So generalizing a sum product network to imprecise probability is in a sense simpler. Here, you see, for each sum node, I have a probability mass function. In the credal case, I have a set of distribution. We generally specify these sets by linear constraints. And basically, you see here we have parameters, but these parameters are constrained by, I don't know, a number of extreme points of these linear constraints. And inference, kind of surprisingly, is not affected by this generalization. So the model was tractable, at least the main inference task can be solved also in the credal SPN. There are some subtleties. I'm making things very naive. But I would say this is an interesting example for which moving to the imprecise setup doesn't make the inferential complexity higher. Basically, you move bottom up. The inference algorithm is bottom up. For each one of these points, you have to solve a linear program, basically. So you have linear constraints and a linear, and then you obtain the lower probability when you move up to the root of the circuit. So these are the credal SPNs. you can use if basically you want to do some sensitivity analysis in some product networks. Okay, now I want to tell you something about the application of this stuff. In the afternoon, I want to talk about causality. Now I want to tell you something about the application to expert systems, so to knowledge-based system for decision support, and also about machine learning based on credal networks. I'm a bit late, so I will be quicker than expected. So basically, we are here. My slides, there are just a few slides. Together with the slides, I prepared some, there are 2 PDFs if you download this material with what I call a gallery. And the gallery are basically longer slides with more information. But probably I have to skip something. Sorry, but it took more than what I expected. And let me just check. I have to finish in half an hour. Okay, I will. Don't worry. So, one, for me, very important and very powerful application is the application to what we can still call expert systems. Okay, this is a bit old-fashioned term. Expert system was the naive idea of an AI that playing chess in the 80s. This was an expert system, or you want a chatbot before the chatbot time you can interact with. Okay, these are not so on hype nowadays. Deep learning is more important, but people is still using this system for the simple reason that data, you cannot have data for any kind of application, and sometimes you could get data, but this is potentially expensive, and maybe asking a domain expert is cheaper than getting the data. So basically, you need this kind of system. And what is good in approaches like Bayesian network, and I will focus, of course, on credal network, is that you can quite naturally integrate different sources of knowledge. So a credal network, a Bayesian network, is this combination of local pieces of information. Maybe for some nodes, for some models, you will use data. For some other model, you will use an expert. For some model, you will use physics because you have a structural equation telling you something. Let me show you in what I call these galleries, some old example. This is what I did a lot with credal networks, but let me take another example. So this was a natural risk assessment. In risk analysis, of course, you might have data, but sometimes you don't have data. Some variables are latent. For some variables, it's too complicated, and you want to ask the expert. This was a graph I listed with an expert involving different factors potentially affecting this, and this was a proxy indicator of an environmental risk level in the area of southern Switzerland. And you know, in our credal network or Bayesian network mapping, what you need is a model for each variable given the parents. For some variable, I ask the expert. For some variable, I use the data. For some variable, this is the peak flow, which is a physical quantity, which depends on this, and this. I add physics. Physics can help me, and I have an equation. So I use an equation. And with this kind of model, you can embed different sources of knowledge in a coherent framework. When you do that, especially if you have equation, the fact that you work with discrete variable is a limitation. So ideally, you should better move to hybrid models where you combine discrete and continuous variables, but still with some additional limitation, you can do that. And eventually, you can have a coherent model, and you can do some risk analysis. Okay, this was the output, and I was telling the expert that this was the basin or river. This is the most risky point in all the area because the proxy had the highest value. But everything was eventually a the computation of a posterior probability. So everything eventually corresponded to this kind of problem. So these are the features I can observe on my system, and this is the proxy indicator of the risk level. Of course, I had the intervals. You discussed the issue related to decision making with interval probability, with imprecise probability. In some cases, I cannot say whether this is dominating this option is dominating the other option. I have to suspend my judgment. But this might happen exactly as if you interact with an expert, you ask his opinion, and maybe in some cases the expert is going to tell you that certainly is not option 3. Maybe it's option 1 or it's option 2, but it's not option 3. And this is not best, but this is totally acceptable. It is probably less acceptable for machine learning people. So my message, as you see, I am going very quickly now because of lack of time, but my message is that credal networks are a very powerful tool to implement expert system, knowledge-based expert system. In machine learning, are very powerful tool to do, let's say, sensitivity analysis. So, but the fact that they can produce indecision between 2 or more options can be an issue, especially if you want to publish in a super competitive machine learning conference. You have to struggle to convince that, okay, in some cases, this kind of analysis is not leading you to a simple answer. There are other advantages, but if you force on accuracy, classical methods, they always give you an answer, even if there are not strong reason to give you this option. In imprecise methods, strictly speaking, in some cases you have to suspend your judgment, and you might return multiple options, which are non-dominated, but not a single one. Just also as a quick recap, I like this example. This example was a kind of system used a long time ago for risk analysis. But if you want, in a sense, is a Bayesian network. And okay, in this sense, is even so there is no imprecision. And if you want, this can be used also when there is no uncertainty at all. So it's really just a logical formula. So there is a system made of different components. So we have the decomposition concept with graphical models. And let's say the failure of the system is based on this simple propositional logic formula. So I have to consider the disjunction between these 3 input, the conjunction. So well, there is a failure of these 3 component, or the failure of this component, the system fails. Whatever. This is a nuclear power plant. No, it's not a nuclear power plant. It's something much less critical. But the failure is dependent on this logical relation based on this decomposable structure. So if you want, this is a logical formula, but you can give the shape of this directed graph. Okay. We are not interested in a logical analysis because in general we have only, so of course if this is true, this is true, this is true, this is the conjunction which is true, and then the disjunction between something which is true and something which is false is true. And so we have a failure. But in practice we only have uncertain information. So what we want to do is to propagate uncertainty. And this, again, for the reason that deterministic model, like my physical equation, are just a special case of conditional probability tables. They are basically degenerate conditional probability table, where the distribution are degenerated. So they are 0, 0, 0, and 1 on the single output. But Bayesian networks can consider determinism as a special case, and credal network, which has a further generalization, can consider determinism as a special case. So for instance, what is the conjunction of 3 events with probability 0.8, 0.8, 0.1 is just the joint probability, 0.8, 0.8, 0.64 times 1, 0.64. So you see, I'm propagating the probability. What about the disjunction between two events, one with probability 0.2 and one with probability 64? Okay, I have to take the product, which is this one, and in this case also I have a failure, but also if this is false, and this is false with probability 0.8, and this is true, and this is true with probability 0.64, I have a failure. And if this is true, probability 0.2, and this is false, probability 36, this is also a failure. So I have the sum of these three guys, and this is the probability of my failure. So you see, this is a Bayesian network, and I have this probability. And these probabilities are the probabilities of failure, which are typically asked to experts, which are they generally are also time dependent, but okay, let's skip this. And maybe my expert is not able to give me a single number. My expert can better give me an interval of probability. Still, this will be a credal network, and I can do a credal network inference to compute that the bounds, so the minimum is when this is 0.8, this is 0.8, and I will get the 0.64. But the upper bound will be when this is 1, and this is 1. And so the maximum is probability 1. So I have this interval of probability. Let's say this is the probability of failure of this component as assessed by the expert. And again, I have to do the sum. I have to do this kind of combination, this kind of inference, for all the possible combination of these intervals. And again, take the lower and the upper bound. And this will be a credal network inference. And I get 64-1. I have to decide whether my system is failing or not failing. I don't have a precise probability of failure, but I know that my probability of failure is bigger than 0.64. So for sure, let's say that this is my decision rule, the system is going to fail because the probability of failure is higher than 0.5. Let's say with different numbers, let's assume that my expert instead of 0.8 is giving me 0.7. With 0.7, the same propagation here will be 0.49, and this interval will become 0.491, which is under 0.5. A little bit, but under 0.5. And so in this case, if my decision is based on probability bigger than 0.5, I should say, I'm not sure. I cannot tell you whether the system is going to fail or not to fail. Everything here is very simplistic. But is a super simplistic example of a credal network, an inference, and a decision based on an inference. And we know that with imprecise probability, decision based on imprecise inference can lead to undecision. You see? Because the other option can have probability, the probability of failure can be 1, can be 0.99, but can be 0.49. And if the probability of failure is 0.49, the probability of not failure is 51. So it's more likely. Please.
Can we reduce the indecision by including second-order information?
Yeah, but this will not be anymore a credal network. This will be a hierarchical model, and this, strictly speaking, will be a precise model. You see, for sure you can, and this would be very reasonable because a person would not be happy say that I'm in the side because of this 49. Come on, this is one. But strictly speaking, if we accept that all are equally it's not right to say that they all are equally likely, because if they are all equally likely, then I have to average and take like the midpoint, and this is not the midpoint. But a good point anyway. Okay, so let me just tell you, I have a short time, but tell you something about what has been done with credal networks for imprecise probability. I think, not sure, with Matthias, we discussed the naive credal classifier, the naive topology. So basically, the naive credal classifier is an example of classification task solved by means of a credal network. A credal network with a very specific topology, namely the naive topology. Okay, this idea was historically the first one, And then it was sophisticated, so we consider more complicated topologies, more complicated model to have better classification tools, still based on credal networks. What you have to do in practice? In practice, once you have your problem, you have first of all decided the graph. And the graph can be decided on the basis of your data, and there are techniques to learn a graph from data. Or, like in the naive case, you can make some structural assumption. In the naive case, you assume that given the class, the features are conditionally independent, which is an assumption, which is not so realistic, but typically it can be okay to have a good, somehow unbiased results. Or you can sophisticate this assumption. And you have the graph. You have the variables, and you have the graph. For instance, the naive topology. Once you have the graph, you need to quantify by means of imprecise probability, by means of credal sets, your local models. For instance, in the naive case, for the feature given the class. What is typically used is the imprecise Dirichlet model, which is a statistical way to learn credal sets from data. Once you have the credal network, you can do classification by querying the credal network. Basically, you compute the probability for the class given the features. This is a credal classifier. With credal classifier, you should accept that the output can be more than a single output. The classifier cat and dog sometimes can tell you that, I don't know. Sometimes I'm sure it is a cat. Sometimes I don't know. It can be a cat or it can be a dog. I'm not able to say clearly that it is not a cat or it is not a dog. Credal classifier, they allow for indecision. Okay. This is totally coherent with this kind of approaches. But the good point with credal classifier is that they are typically very good in discriminating hard to classify from easy to classify instances. Let me just show you an example from this, what I call the gallery, which is linked to the PDF. So here is a lot of material, but I don't have time. I'll share this with you, but I don't have time to. And so, let's say this was, for instance, the naive credal classifier. Let me say. This is the point. So this is the credal network classifier. If you have a credal network classifier, basically you have also a collection of Bayesian network classifier. The credal network classifier can be indeterminate. The Bayesian network will always give you an answer. Okay. So an interesting experiment, but is more than experiment, is to check the performance of the Bayesian network classifier on two different groups of instances. On the instances which are determinate, so on the instances for which the credal classifier is giving you a single instance, and on the indeterminate instances. So you have two groups of instances if you use a credal classifier. And if you check the performance of the Bayesian network classifier, you will typically see a huge difference in terms of accuracy. So if the credal classifier gives you a single output, it is very likely to be the right one. If the credal classifier tells you, I don't know, very likely the Bayesian classifier will be wrong. And this is somehow not surprising because it means that the output is not robust with the choice of the prior if you work with the IDM or whatever. So if you want to use this model in machine learning, basically what you can take advantage of is a kind of pre-processing. You can better decide which one are the instances, the prediction you really trust, and the ones that you don't trust completely because you see that they are not robust. And that's why your conservative approach is telling you, I don't know. You see, so what I want to emphasize is that to apply credal approaches in machine learning, is very, very specific. Somehow, okay, it's very general. It makes a lot of sense to use these approaches if you have a few data. It makes a lot of sense to use these approaches if you have missing data, and if the kind of missingness is something you cannot make assumption. The reason, you don't have a clear explanation of the reason of the missingness. But in the general case, you can use these approaches as a pre-processing, basically. So, and okay, also as a personal experience, I will tell you is not trivial. To the machine learning conference are very, very competitive. These approaches are still, let's say, not. I would say they are not at all controversial, but for some people, they are not used to these approaches. So it's even more complicated to get your paper or whatever accepted, because they first need to be convinced of this credal idea. It's possible. There are, especially in the last year, paper accepted of very competitive conference like UAI, NeoRIPS, where some people is here, some people also, Michael Meyer is doing something very effective. There is also a guy, Michele Caprio, having good papers in this very competitive machine learning conference. So is totally doable, but it might be complicated. And my experience, I just had now a paper, relatively good for this community UAI conference, also with some other people here published. I think we have this feeling that we always have to find the analytical exact solution of the optimization, while the machine learning community is not that focused. It's like, okay, we have a problem, we formulate the problem, and then the problem corresponds to an optimization. Okay, in machine learning, this distinction between modeling the problem. Modeling the problem is something, and then you have to solve the optimization. And sometimes they use some approximate techniques. And to prove that their approach is good, they use experiments. And while I think we are very focused on finding the analytical solution, which sometimes is very complicated, if not just impossible to find. And for instance, I had a paper on UAI this summer on qualitative constraints with Bayesian network by relaxation for credal network. And this paper was accepted at UAI, but we just used, we formulated the problem, the experiments were good, and the solution was based on some standard numerical technique. This paper will be something, I'm not sure I would have submitted the paper to SIPTA, because I was not that confident about the elegance of this paper, and it was accepted in this super competitive, not super competitive, but competitive machine learning conference. So my message, no, I'm really going too far, is really just, for sure, it is cleaner in the way you formulate the problem, distinguish between the problem formulation and the solution, and then the experiments. The experiments should always be good, otherwise it makes no sense. The analytical solution part sometimes can be based on standard solver and still can be convinced. And I'm really focusing on these machine learning communities. Okay, so this was just a side message. Maybe also we can discuss offline. And why I'm saying that? Because I tried so many times to use EDM, quantification, on credal networks for machine learning. And the optimization problems I had to face were sometimes very, very complicated, with more complicated topology. With the naive, you have an analytical, not analytical, because then you need the linear programming, but you have a clean solution. In other cases, much more complicated. And if you want, the reason is that because when you learn a credal set from the data, typically you have different credal sets which depends on the same parameters. And basically, you cannot optimize the different credal sets in one independently of the other. And so this is an additional complication. You can ignore these dependencies, but if you ignore them, your result will be very imprecise. So this is a limitation about applying machine learning to credal model. And just to finish, let me say, I have 3 minutes, no? Something like that. Just to finish, still in this gallery, I think what is an interesting point is about evaluating a credal classifier. So let's say that you have your credal machine learning techniques, you're writing your paper, and you want to show that your results are good. But most of the people is going probably to use a precise model, and you're expected also to do a comparison against a precise model, and to show you that you are better. But there is a substantial difference. So let me use a super stupid example. No, which is... so let's say that you are 2 doctors, and you are asked to make a diagnosis. Sick or not sick, whatever. And you are called Dr. Vacus. And your answer is always the same. You always say, I don't know. I don't know. You do some exam and say, I don't know. You can be sick or not sick, I don't know. And you are Dr. Coin. And Dr. Coin just toss a coin and sometimes say you're sick, sometimes you're not sick. Which doctor you trust? I would say you are not very good doctors, but which one would you trust more? Dr. Coin or Dr. Vacus? I don't know. And let's say if you are very analytical people, you say, okay, let's consider the expectation. Let's say the losses. Which are the losses? Okay, let's say a wrong diagnosis is not symmetric, but is maybe 0, 1. So a wrong diagnosis is loss 1, a right diagnosis is loss 0, or vice versa. And let's compute the expected value. But I can only compute the expected value for Dr. Coin, because Dr. Coin is always giving a single answer. And so the expected value will be 1/2. If the coin is unbiased, the expected loss of Dr. Coin will be 1/2. What about Dr. Vacus? Some people use a kind of discounted accuracy. I could say, Dr. Vacus is telling me many options, but one of these options is the right one. Okay, but this is too easy because it's giving me all the options. And anyway, so if he gives me, let's say, many options, I will say that this advantage of 1 should be divided by the number of options. So the advantage I got from your diagnosis would be 1 if you give me a single option. If you give me 2, I have to discount this advantage, and so I will say I got 1/2. So the utility I got from you, if I accept this, will be always 1/2, 1/2, 1/2, 1/2, 1/2, and your utility is 1/2. So from the point of view of expected utility, you are the same from my perspective. So which doctor should I prefer? If I only consider expected value, you are the same. But I don't know you, but I would prefer Dr. Vacus, which is not that such a good doctor, but I prefer to remain in a situation of indecision rather than accepting a potentially wrong, potentially very wrong 0.5 diagnosis. And to express the difference between these 2 doctors, expected utility is not enough, and I have to. My reason to prefer Dr. Vacus is the variance, because with Dr. Coin I have a lot of variance, because it can be 0, 1, 0, 1, 0, 1. The expected value is 1/2, but the variance is higher. With Dr. Vacus, basically I have no variance. And no variance is like to say that I don't want variance, I'm risk adverse. And typically most of the people is risk adverse, and that's why somehow I should prefer Dr. Vacus to Dr. Coin. I'm done, and this is just to say that if you need a metric to compare a credal classifier against a Bayesian classifier, if you use this utility discounted by the number of classes, somehow you are probably penalizing too much the credal approach. And there are proposals about some utility-based accuracy which try to take into account this lack of risk aversion that you get with the credal approaches. But still, if the goal is eventually to make your paper accepted, it can be not enough, but I think is a very reasonable point in favor of credal approaches. That's it. Sorry, I would like to. I skipped a lot of material, but okay, this was the general ideas I wanted to report to you about credal machine learning, credal expert system. In the afternoon, I will move to causality. So it will be 1 hour, but fully focused on causal analysis, again with the credal network. Thank you, and sorry for the mess. Thank you. Okay, guys, so maybe we can start. So we were here, we stayed here for a lot of time. Now we want to go here. So you know, the causal analysis, the story, it started from Bayesian networks. Bayesian networks are not causal model. They just describe a correlation. We were discussing if you have an arc between A and B, you might be tempted to say, so A is causal cause of B. There are algorithms to learn from a data set, a graph, a directed graph. But if you believe that this is clearly saying that the orientation of the arcs has a causal meaning, you might be very, very wrong, at least in general. So these are not causal model. But of course, people, especially Judea Pearl, try to expand these theories and basically moved from Bayesian network to so-called structural causal model that are in the same time a special class of a Bayesian network, but somehow they extend the formalism and the power, the expressive power of Bayesian network into the direction of causality. This is like the mainstream, if you want. As said, some people extended Bayesian networks to imprecise probability. We discussed what these credal networks are. And what is interesting from my point of view is the strong connection between credal networks and structural causal model. And basically, my point is that the knowledge, this structural causal model involves some latent variables that you typically cannot observe, that act as a confounder between your model variables, and the kind of knowledge you can assess from the data you have that are not directly involving this latent variable is imprecise. So basically, you can assess from this data an imprecise probabilistic model. So basically, credal networks. A second. Credal networks and structural causal models are the same, or maybe this is too much, but they can be. You can solve some causal analysis by means of credal networks. So let me try to say what is a causal analysis about. You know this picture. This is from the book of Judea Pearl. There are 2 recent books on causality. As usual. Sorry. This was the classical book. This is quite tough also. And these are more recent book, and especially this one. This is a primary. If you're interested in causality, I think this very short, very compact book to start with causality. And let me also say that I'm focusing on causality from the perspective of Pearl, which is based on graphical models. There are other causal theories that are not explicitly considered graphs. Most of the results are almost equivalent, but maybe people working in this field will not completely agree. But let me just say that what I'm doing is causal analysis in the formalism of Judea Pearl, which is, of course, one of the most popular ones. Let me comment this picture, which is quite popular, and this concept. So there is this concept of the ladder of causation with like three different layers, three different levels. And it's about, if you want knowledge, the kind of knowledge you might want to answer when doing what? Let's say science. Somehow this is kind of approaches. So you want to do, and we start from the bottom. And let's say in the lowest level of this ladder, we cope with observational information. We collect data from an observational study or whatever, and we already discussed what we can do with this study. We can learn a probabilistic model, and we can use this probabilistic model to answer predictive queries, for instance, correlational queries. But when we discussed about machine learning, deep learning, this is very good for technology. We wanted to do good predictors of whatever, but we should be more ambitious. So this is just the first level. We wanted to answer a question like, if I see this, what can I say about this variable? And this, if we have enough data, we can compute a correlation. We can say very likely, like in large language model, if I already was writing this and this and this, what is going to be in the next paragraph? And okay, maybe by using a lot of textual data, I can predict something very good, and my GPT text can look very realistic, very, very reasonable, if not very good for some application. But we can do more than that. And we can move up and move from the pure observational level to the so-called interventional level. So we can do something different. It's not just record observation and write the results of different observation in the data set, but we can decide the state of some of our variables. We can do an intervention. An intervention is something completely different from an observation. In one case, I collect my entity, and I observe that one of the state of the variable interest is this one. In the other case, in the interventional case, I'm the faculty of changing the state of these particular variables to a particular state. Okay, this is, for instance, what is done in the field of reinforcement learning, where I take action, and action is deciding that the state of this variable is going to be this one. You see? And I'm interested in interventional queries. So I'm not only interested in, say, okay, if I observe that y is this, what is the probability for this other variable? But I'm interested in what is the effect of an intervention. If I force a variable to a particular state, what is going to be the probability for another state of another variable? And these two answers can be, at least in general, different. So this is interventional level. And there is an interesting paper, not by Judea Pearl, but by Elias Barenboim, which is the former student of Judea Pearl, and now I think is the guy doing the most interesting things in causalities in Columbia. In New York, he has a group, a very large group, working in causality. He proved that these three levels, and I will go to the third level, are disconnected in the sense that if you derive a formalism to answer this query, for instance, Bayesian network, joint probabilistic modeling, this is not enough to answer these queries, at least in general, to move up to the ladder. For interventional query, we need something more. And we can move far up to the counterfactual field. And counterfactual field is like doing a query about, it's basically doing an interventional query. So what is the effect, what happens if I take, I don't know, some some medicament, or if I do something, given an alternative reality. So, for instance, in the real world, my patient didn't took the treatment. What would happen if he would have taken? So, what if I had done something, provided that in reality I didn't? So counterfactual has to do with two different alternative worlds. The factual world, where something happened, and the counterfactual world, where something which is contradictory with respect to what happens in reality. We know how to compute conditional probabilities, but we cannot compute a probability of y given x equal to 0 and x equal to y. This is a contradiction. This is not anymore a contradiction if we consider two different worlds. The factual world, where this is an observation, and a counterfactual world, where this is an intervention. A counterfactual, a simulated intervention. What if I would have done this? And it's clear that we need a dedicated formalism for this kind of queries, which are on the last layer of causation. And this is basically what this has to do with a deeper understanding of the reality. This has to do to explaining the consequence of a causal model. And this, if you want, has to do with sciences, the most ambitious kind of queries we can ask ourselves. So, what I wanted to emphasize in this last module is that imprecise probability are very strongly connected, and credal networks are a powerful tool to answer counterfactual queries. Of course, counterfactual can appear very, let's say, esoteric objects, but in fact they are not. Are really just what I told you, so considering two different realities, but they should obey somehow the same laws. So we see that there will be two different models, but somehow connected. And the key to connected will be a set of latent variables common to the factual and the counterfactual world. And what we will see is that these models are going to be credal. Basically, they are credal networks. Okay. So now I have one slide with a minimalistic example, but I think if you get this minimalistic example, we are happy. I'm not stopping after this slide, but this will be most of the of what I wanted to tell you. And let me define what these structural causal models, à la Perl, are. So let me start from a variable which is not latent, which is manifest, a variable we can observe, a variable for which we are going to collect data. Let's say this is x, and I call these kind of variables endogenous. So these are part of my system. And this is my variable x. Very stupid example. Well, let's say that x is a Boolean variable. Okay. Let's say that I collect observational data about this variable, and I'm able to learn a probabilistic model. Can be a Bayesian network, can be whatever. In this case, it's a single variable, so a probabilistic model is just a probability mass function. Is a Boolean variable is enough to say that the probability of the first state is p, and the probability of the second state is 1 minus p. Probability mass function. This is my observational knowledge. Okay? This has to do with statistical learning. No, just statistics. But let's say that into the game we also have an exogenous variable. And for me, exogenous means latent, a variable we cannot observe. Let's say this variable is u, and let's say that u is ternary variable, for instance. And let's say that we have a connection between this variable, a strong connection between these two variables. So let's say that the state of x is determined by the state of u through a deterministic function. So for each state of u, I got a different state of x. So for the, say, u is quaternary, sorry, I have four states. The first two states, they go to x equal to 0, and the last two states, they goes to x equal to 1. This is what I call a structural equation. Okay, this is not a probabilistic model. This is a deterministic model, no? Because the structural equation is determining the value of x once I know the value of u. Okay. The problem is that u is a latent variable, so I don't have information about u. I cannot observe u. I cannot collect data about u, while I can connect data about x. So, given u, I get x. Given a distribution over u, I can obtain a distribution over x. This is what some people call total probability theorem. It's just conditioning. So the marginal probability for x is the probability of x given u times the probability for u. This will be the joint summed. Sorry, this is the sum over u. I will fix the sum over u. But remember, this is a conditional probability, but the relation between x and u is deterministic. So this conditional probability table has degenerate values, has 0, 1 values. So this conditional probability basically is a delta, is 0 when x is equal to the value of the function for u, is 1 in this case, and 0 otherwise. You see? Okay, because of that I can say that if I have a distribution over u, I can obtain a distribution over x. A state of u induces a state of x. A distribution over u induces a distribution over x. But in reality, what I observe is not a distribution over u, it's the distribution over x. So I should not move from PDU to P of x, but from PDX to P of u. Small problem, the mapping is not invertible. You see, we have many, this happens in general. I have many states of u going to the same state of x. So if I invert the relation, in generally there is more specification of P of u giving P of x. And we can check this analytically. So you can see, in this case, it's very simple. So you see, this a generic distribution parameterized by P such that the first two states, they got P half, P half. And the last two states got 1 minus P half, 1 minus P half. All these guys, they generate a P of x, which is such that P of x equal to 0 is P. But this guy is a credal set. So what I'm telling you is that if you have the model with the structural equation, and if you have the observation over x, you can back propagate from x to u this probabilistic information. But this is not one-to-one mapping. So eventually you don't get a P of u. You get a collection of P of u. You see, it's a one-to-many mapping. And so you get a clear set. But come on, if with a complete precise specification, this is a Bayesian network. With a clear set here, this is going to be a credal network. And this is an object we can use for causal inference. This is basically my point. Okay, please. Good point. No, this is simplistic. This is very simplistic. Well, somehow, you know, if you give structural causal models are basically the same, but with multivariate models. So I have many variables, I have many latent variables involving confoundability. Here, if you want, in this simplistic example, I'm merging together all the latent variables together and all the manifest variable, all the endogenous and exogenous. I use this notation. This is not completely wrong, but what I lose is the independence between the confounders. So in a sense, this can be done also in the general case. Of course, the real computation in this way becomes unfeasible, or at least becomes exponential, because I'm merging together all the variables. I'm not exploiting any decomposition property. First problem. And the second problem is that I'm losing the independence between the confounders. And this basically corresponds to an outer approximation, because we will see the typical inference, counterfactual inference, are interval valued, and so in this way I obtain larger inference. But we try to do that locally. So this was just to illustrate the general idea. Okay. Now, so this is just to tell you that in practice, structural causal models are a sophistication of this setup. But still, okay, now we are familiar with Bayesian networks. What is a structural causal model? At least an important class of structural causal model is like a Bayesian network such that the variables that are non-root and the root variables are the parentless variables. The parentless variables are assumed to be the exogenous one, the one we don't observe. The non-root nodes, like this one, are assumed to be endogenous variable. And for this endogenous variable, we assume that we have the structural equations. So for these variables, we assume that they are determined by their parents. This is the setup. So basically, we have a graph with a causal interpretation. And this is something, for instance, you don't have in the field of Bayesian network. So this is coherent with the ladder of causation, because if we only have the data, we should stay here. We cannot move up. To move up, we need some additional information. So besides the observational data, we need something more, and this something more is the causal graph, is to know what is determined by what, including confounders, external unobserved confounder. So another big problem is how to find the causal graph for your problem. This is very often done by experts. There are techniques to learn the causal graph from data, but generally you just learn a class of causal graph, which is an additional problem. So I'm doing things very simple here, but here I'm implicitly assume that some expert or some source of information already gave us the causal graph, and I'm also assuming that the structural equation is available. So I know how the state of the endogenous variable are affected by their parents. Is this always the case? Not always. Clearly not always. So, especially if you consider that some of the parents can be latent variables, it's not so obvious to find which is the equation, the structural equation determine the state of a variable given something which is latent. Okay, let me just skip something, then I will go back to tell you. And we have this problem. I'll go back to this later, but we have. A second. Okay, yeah. So we have the problem of finding the equations. And okay, we can always say, if you have an expert giving you the equation, you are fine. But let's say that this is not the case. What you can do is to be conservative. And to be conservative basically means to enumerate all the possible deterministic relations. And this can be done. So let's say, for instance, that we have this slice of network, where B is a variable we can observe, A is a variable we can observe, and U is a latent variable. A and U of B are the parents of B, you see? So this is a deterministic model. So we know that B is a deterministic function of A and U. Okay. We can say that for each value of U, there is a deterministic relation between A and B. Now, say that A is Boolean and B is Boolean. How many possible relations can you imagine between two Boolean variables? Let's say B is a Boolean variable which is a function of another Boolean variable. How many possible deterministic relations we have? 4, namely, it can be constantly false, constantly true, it can be identity, or it can be negation. So we have 4. If we set 4 states for the U variable, for each one of these 4 states, we have one of these 4 mechanisms. And this is a structural equation. This is, if you think, is the most general structural equation, because any other equation would be just redundant. I can imagine a U variable with 5 states, but the 5th state will be just a replica, a clone of one of the first 4. So this is something, this is a trick, if you want, to enumerate, to quantify the structural equation when you don't have such a structural knowledge. There is a problem, so this is exponentially large. So you need a lot, an exponentially high number, even if it's still local, an exponentially high number of latent state to enumerate all. Okay, with 2 variables is trivial, but if you have many parents with many states, it might be complicated. So this is, if you want, the relation you have. But okay, in some other case, you can start from this conservative, and maybe you can try to ask your expert, but okay, this relation is the identity, but I will say that it's impossible that B is just a clone. So maybe you can remove some of the deterministic relation, which means you can remove some of the latent state. But okay, let's say that in my first slide, I made everything very, very easy, but I'm already making some assumption, no? Yeah. In fact, I can tell you we are still working on some other way to learn the structural equation from the data by finding, so, because we can do not a real learning, but for that we need an exponential number of latent states. So let's say in practice, if we have a bounded number of latent states, a challenging problem is to find which is the best way, which are the best equation considering the kind of data you have. Okay, so this is a bit, and as usual, I'm focusing on the discrete case. Of course, structural causal model have been defined also for the continuous case. We have some results which can be extended to the continuous case, but we didn't in a paper. We are working on it, but it requires some formal work, and there is something to do. And so let me observe that if you are now okay with Bayesian network, a structural causal model is a Bayesian network, a bit special, because if for the nodes that are non-root, the conditional probability table is degenerate, is made only of 0 and 1s, while for the root nodes we have probabilities. And additional problem, this probability over the latent variables are not available. We don't have data about these latent variables by construction, but we have some idea to back propagate the information about the manifest variable and obtain some imprecise information about these latent variables. Okay, so let me start from the bottom of the ladder. So we are on the first level, and so we just use our structural causal model to answer observational queries. This is very simple. We already know that we don't need the confounders. We don't need the latent variable to answer. If we have data about the non-latent variables, we just learn the model. For instance, we learn a Bayesian network, and then we are able to answer observational queries. Observational queries are queries not involving intervention, not involving counterfactual. All the stuff, we did it. We did some conditional probability, but as I told you, this can be very misleading if you assume that this kind of relation have a causal meaning. So you can like to say, okay, this is clearly telling me that the treatment has not a positive effect on the patients, but it's not that obvious, and there are lots of situations for which you can prove that the observational analysis can lead you to a wrong causal conclusion. This is also related to what people call the Simpson paradox. This is from the book of Pearl. You see, these are aggregated data about people doing exercise and the level of cholesterol. And if you do, I don't know, a linear regression, you will see that. And this tells you that the more exercise you do, the more cholesterol you have. So stop doing don't go to kayak in the afternoon because it's dangerous, it's very dangerous. That's why I'm not coming, because I know. But if you condition of some other variables, so these are not completely synthetic data, but there is something. But I think in this way they looks very nice, but it's not that that nice. But okay, here is just to show that, say, if I do conditioning also on the age, I will say that this is my explanation. As people get older, they start to be concerned about cholesterol, about the end of life coming soon. So they start to do a lot of sport. Not sure it's really true. It's really like that. But so you see, in this way you can explain what is probably the real pattern. So the more exercise you do, the less cholesterol. And the idea is that. If you put the aggregated data, maybe you have a conclusion. If you disaggregate by conditioning on some other variable, you get completely different conclusion. This also is very famous. I don't know. This was data about potential gender bias in Berkeley. Berkeley is one of the most liberal universities in the USA, in the US, and there were very different acceptance rate with respect to gender. So then if you disaggregate with respect to the faculty, you see that, in fact, there is not such a huge difference with respect to gender. But it's just that women applied to more selective faculties. So this was at least the explanation. But they are just different variants of the same paradox. I think also during the COVID, there was something like that about vaccinated and unvaccinated. This is also called the Simpson paradox. Just to say, don't trust observational data if you want to do conditional causal analysis. If you want to do predictions, this is perfect, but not for causal analysis. So if we move up to the ladder of causation, say that we want to do an intervention and intervene of a variable. Let's say we want to intervene of x. This is the causal graph. In this case, you see the u are the latent variable. In this case, we don't have confounder, latent confounder. So each variable has a latent variable, which is a kind of noise term, but it's not confounding. But okay, we have confounder at the observational level. And doing an observation basically means that x is not anymore a deterministic function of its parents, of u of x and of z. But the state of x is defined by an external intervention. So from the perspective of the graph, you do what they call a surgery. So x is not anymore affected by its parents. And all the terminology was mutilation, which sounded a bit wild, but was like to say that we are really changing the graph. And this is the intervention. And then once you do the intervention, this is just a standard query. But this is a standard query. This will be a Bayesian network query. So what is the probability of this given this intervention? But the interventional query involves this latent variable. So it might be the case that you don't have data about the u variables and you cannot answer the interventional query. Again, this is perfectly consistent with the ladder of causation. We know that we moved up and the data alone cannot be enough to answer the question. But the data together with the causal graph can be in some case enough to answer the interventional query. Not always, but in some cases it is possible. Basically, in this setup, once we do the intervention, we don't have data about u of z and u of y, which are the latent variable. But we can marginalize them, and we can basically obtain this expression. And this expression is interesting because this is a causal, this is an interventional query, and the answer is based on this combination of probabilities, but these are probabilities involving only the non-latent variables. And we have data. So we can use the Bayesian network, we can use the data to answer this query. And this is what the so-called do calculus of Judea Pearl can do. So do calculus is about answering causal query by means of observational data. This is very good. This is very important. But causal do calculus is not general. So there are queries that you cannot answer in this way. Even if you have the causal graph, we need the causal graph for do calculus, but even with the causal graph, you cannot answer all the queries. And this is especially the case for counterfactual queries. And to model a counterfactual query, you have basically to duplicate your variables, your observable variables. So x and y, we have in a counterfactual setup, we have duplicated these variables, because this is the real world, this is the real world, this is the counterfactual world. And in my counterfactual query, I'm considering, for instance, what is the probability that the treatment gives, in the reality, I did the treatment and the effect was negative. What will happen in a counterfactual world where I will do the treatment? So you see, this is counterfactual. I need to duplicate my variables. But they are connected, and they are connected by the latent variables. This is what some people call twin network, because the non-latent variables are duplicated. But it's a single coherent model because they are both affected by the non-latent variables. You see? According to the ladder of Pearl, if you have the equations, if you have the causal graph, and if you also have the equation, you can answer this kind of queries. But still, to answer this kind of query, you need to quantify this model. And this model is quantified by the equation, but it's quantified also by the marginal probability of the latent variable. And to get this marginal probability of the latent variable, you need this kind of back propagation. You should take your data, back propagate them, and get the probability of the latent variable, over the latent variables. So now I try to show you how you can do that in a not completely general, but partial, non-generally general setup. Let me start from this model. Again, this is here we don't really have confounders, but this is a model where each one of these four variables, which are observed, A, B, C, and D, is affected by the parents and by a latent variable. Okay. The data are about A, B, C, and D. Okay. And we have the conditional probability table, which are basically the structural equation, this function f of A, f of B, f of C, f of S, whatever. We have data, and so if we have data, we can say we have a joint probability mass function over A, B, C, and S. We need to do this back propagation. We saw how to do this with a single node, a single latent and a single manifest. Let's see how it works in the general case. So in the general case, basically, we should make explicit the fact that this model generated our data. And basically this means that if I marginalize out the U variables, the corresponding model should be compatible with the data I observed. So if I sum out U of A, U of B, U of C, and U of S, I have to obtain, so here I'm taking the joint distribution, which contain the marginal about these U variables, which are the root node, and this delta is 0, 1, depending on whether this is equal or different. These are my conditional probability tables. So this is the joint model. I'm summing over the U variables, so I'm doing a marginalization. And the result should be a distribution over the non-latent variables, so A, B, C, and S. And this distribution is what I observe from the data. So you see, basically, this is observed, this is known, and this is unknown. P of U, P of UB, UC, and US are unknown. So this is like a compatibility constraint. My model involves latent variable. I don't know the latent parameters, but I know that the latent parameters should give me a model which is consistent with what I observed in reality. What is bad in this relation? This is a constraint, but this is a non-linear constraint, because the unknown are the P of U. So you see, is non-linear, and is in some senses global. So it's merging together all the variables of my model. I would ideally prefer a constraint which is linear instead of non-linear, and local instead of global. The good news is that with this topology, and this is what I call a Markovian model. A Markovian model is a model without confounders. So the U variable, each non-latent variable has a U variable, but is separate from the others. So in this case, it's very simple to separate, to show that this global non-linear constraint is equivalent to a collection of local linear constraints. And basically, these are the constraints I induce, but it is an equivalence. So these 4 constraints, which are more than 4 because we have to consider all the joint state, is equivalent to this constraint. And you see, now I have a separate constraint for each P of U, and the constraint is linear with respect of the P of U. And this, for me, is just a credal set specification. These are the linear constraints specifying the credal set of U of A, of U of B, of U of C, and of U of S. You see? This, for me, is very interesting results, because basically, if I have the data and the equation and the graph, I can obtain the credal network. And I can use the credal network to answer any counterfactual query. The most, let me this I can do so for instance intervention. The most interesting query for me is the counterfactual. So in the counterfactual, I have to duplicate the variables, the observable variables. But again, this is a credal network. The surgery, the fact that I cut some of the arcs, is basically related to the separation properties. And if I work with my strong or complete credal network, I have the same properties. So nothing really changes. And basically, my causal query becomes a credal network query. Is it better in the sense that the problem is simpler? No. Credal network inference is a hard, is a hard task. But we have like 20 years of dedicated algorithm for approximate credal network inference. And we take advantage out of it. And I think also this is not only a technical, we have a library, which is this one. Remember, Crema was the library for credal networks. Not surprisingly, we used the library for credal networks to create a library, still Java, unfortunately, we're still doing the porting to Python, for a credal counterfactual analysis based on this mapping. And I would say it's not only the fact, okay, that we have a credal network algorithm, but also is the idea that there is a set of distribution, because the mapping is not one-to-one, but is one-to-many. This is my feeling, but it gives you a deeper understanding of what these causal model are. So for people from this community, when you read something, they call this also partial identifiability of counterfactual, bounding counterfactual. Everything sounds very obvious, very familiar, while for people with background in, let me say like that, precise probability is quite surprising. And they have the impression that these bounds are related to some approximation. So you compute bound only because approximation. But this is not really an approximation. It's not that we have a counterfactual which is interval valued because we don't have enough data. It's not about that. It's really intrinsic to the model. It's really intrinsic to the fact that the structural equation cannot be inverted, at least in the general case. So that's why I think this is a promising line of research for imprecise probability, and for having this imprecise probability used also in different domain. If you want to, this is an example where imprecise probability theory is like a technical, let's say, a package to be used to solve another class of problem for which these people, they lacking some formalism, basically. And okay, let me just tell you that this strong idea, for people working with belief function, Dempster-Shafer theory. I don't know if some of you is in this field. Belief function can be described as a special class of credal set. So if you define for a discrete variable a belief function, you have equality constraints, which are linear constraints. So it's a credal set. The kind of credal set we define here are basically belief functions. So because they have to satisfy these equality constraints. It's related to this mapping many to single. So this is just a characterization. It can be appealing. You can characterize the number of vertices, even if this, in the worst case, is exponential. So just a side note, but it has some interest. But let's say this derivation, we got this derivation from the Markovian case. And the Markovian case means that there are no confounder. With confounder, basically, you can do that. Is what we discussed. We are like merging together two nodes. It's just is really just that you have a higher dimensionality because you are merging together two or more variables. So we extended this idea to the general setup. But let's say if you have a confounder involving many variables, the dimensionality of this latent variable can become really huge. And so then we have a computational problem with the credal network algorithms. And that's why we tried to find some alternative inference. And this is basically based to the EM algorithm. So this I will skip. The EM algorithm is a classical procedure to cope with missing data. So if you have data that are missing, they are missing in a systematic way, and we have missing data because our latent variable are missing, and they are missing in a asystematic way because they are always missing. We can try to find, let's say, the specification of this latent variable, the completion of this latent variable, which becomes compatible with the data. And this is like to maximize the likelihood. So the EM is a technique to maximize the likelihood. So basically, to find which are the value of these U variables to have a result which is compatible with the data you observe, basically. So it's not surprising that we can use EM for this kind of application. There are two interesting points. One point is that we can prove that in general the EM only gives you a suboptimal solution. So it gives you a maximum of the likelihood, but it's a local maximum, generally speaking. But what we were able to prove, which is I think interesting from our perspective, is that for these problems, the likelihood is unimodal. So there are no local maxima. There is a single global maximum. And so EM always gives you the optimal solution, which is good. Then there is a point that you don't have a single distribution because we know that there are many models that are compatible with the data. We know that there are many P of U compatible with P of X. So what we do in practice is to run the EM depends on initialization. We run the EM many times. Every time we got a different point, but all these points are maxima of the likelihood, and they are basically the point, they give us a Bayesian network which is compatible with the credal network. So for each point we compute the inference, and then we take the minimum and the maximum, and these are the bounds. But this is an approximated technique, and this is an inner approximation. So the true bounds will be obtained in the limit of an infinite number of samplings. We get an inner approximation. But we have some result about the quality of this approximation, and I think we get a good approximation, at least for the models for which we have a ground truth, but we have also some theoretical result. So if you want, this is suggesting also something like you can do a credal network inference by sampling. This is a bit more than sampling because it's sampling plus propagation, and in this way we got a good approximation. So let me just show you, this I'm skipping, this was just about coping with biased data. So we were assuming that our data are IIAD. In some cases you have bias, so for instance some data you cannot observe. And we show that this thing of the maximum of the likelihood, the thing of the AM, also for biased data. And this is good because in the same way, you can also cope with hybrid data. Say that you are doing some clinical studies. So in clinical studies, maybe these are like interventional data, but maybe from one hospital you collect a family of interventional data. From another hospital, you collect observational data. And you can put all this data together and then obtain and back propagate all the information and obtain a single summary which is more informative on the latent level. So, and you can do that again by the EM in an automatic way. So this is really just to tell you that this to me is a very, very promising direction for credal approaches in the field of graphical modeling. In fact, I'm spending a lot of energy on this field. We are writing some papers. Okay, as everybody nowadays is supposed to use large language model for something. we believe that, in fact, we have some paper about also kind of negative results. So they are good to summarize. For instance, we use this for medical application. But now there are many empirical papers showing that they are not so good in inferring causal relations. So we need the causal graph. So an idea was to use the large language model as an expert and ask him about the orientation of the graph. Of course, the model is not good. It's an observational model based on lots of text data, so it's not good in doing that. But if you use, for instance, medical data, medical papers, whatever, is good in parsing causal statement, and in this way, the kind of causal graph you obtain can be reliable. And this was one of the problems we have. The other problem is to assess the structural equation, and we can be conservative, but to be conservative we need very high cardinalities, and we are trying to learn, let's say, models with bounded cardinality. So this, and again, here everything is on the discrete case. Especially for this model, the extension to the continuous case is it's simple. I still have to write the paper. Can be done. This property of the EM is not affected by the fact that the variables are continuous, but basically are observed because of the manifest variable. So it might be extended, but we still have to do. This is just to give you the feeling of the kind of causal inference. So the counterfactual inference. This is called the probability. Let's say we have a problem. This was a problem related to mental health application. And basically we were interested in checking which one between these three variables was the one mostly causally affecting this variable of interest. This was a bit, I'm not entering the details. It would be a long story. But a typical counterfactual query is this one. And this one is, what is the probability that the effect is true in a counterfactual world where I intervened on a variable, making it true, and another world where my intervention was on the other state and giving this variable being in the other state. So, for instance, what is the probability of being sick without the treatment and being non-sick given the treatment jointly? This is called the probability of necessity and sufficiency, and is very commonly used as a causal descriptor. So we can measure the causal strength of these three variables in terms of this PNS query. which after the credal mapping is a credal network inference. Of course, as a credal network inference, the output will be an interval. 1, 2, what is the third? Third. But even this model, which was very large because you used a conservative specification with lots of variables, so it took 1 day to compute the inference, we were able to see that one state was, one variable, one interval was clearly dominating the other two, so we were able to draw a causal conclusion from the model. You see? Of course, if your intervals are overlapping, it might be that you will be undecided. But this is kind of accepted in this community because we know that the problem is partially identifiable. So you might have interval, and this interval are overlapping. If you want, using the language of Matthias, here I'm using interval dominance. So to decide which one is the optimal option. And this interval is dominating because 0.3 is bigger than 0.10 and 0.3 is bigger than 0.10. You see? Okay, I'm almost done. Okay, just to mention that I will be around tomorrow on Friday, so if you have a question, just stop me, ask me. Feel free also to write me if you're interested in this stuff. I'm very, very much interested in this stuff. And also the project, I will be on Friday. Okay, the project, I'm very focused on this causal stuff, so if there are other ideas we can discuss. But my proposal for the project is to use some data set. We can use the X, Y, Z about gender, treatment, and effect data set I show you this morning. Or if you have another data set, you can use, we can use your own data set. And what we could try, but I'm here also to support you, would be, let's define this causal graph with some discussion. Let's define the equation, which basically means let's quantify the graphical model for this data. Let's try to do this back propagation and to see whether we can compute some counterfactual. So for instance, we wanted to see how affecting is the treatment in terms of the effect or whatever. So we can do any query. So it's very, very open, but I know that especially this last slot was not very technical, but I can support you, and maybe we can use some Python line of code. We can also do that by hand and try also to draw some number. Of course, will be a very preliminary analysis, but if you are interested on Friday, I will be happy to help. That's it. I think it's time to stop. So have a nice kayak session, and see you tomorrow. Or if you have a question, just let me know. Not sure. I'm done. Thank you. Thank you.